Howdy everyone, I'm Michael Pyrcz, and it's my pleasure to be able to join you all for a tutorial on open source spatial data analytics in Python with GeostatsPy. So this is what I'm going to cover right now in this short set of slides. I hope it'll go pretty quickly. I'll talk about just the course, who I am. I'll just have a couple of slides. I promise not a lot of slides of bragging. I'm sorry, just who I am so you know who you're talking to and my experience. I'll get into an introduction of what GeostatsPy is as far as a Python package for spatial data analytics. And then I'll give you the plan. What are we going to do in the next 3 hours together? And I think we're going to have some fun together. I'm excited about this. I'll talk about what you need to do to get set up so you can join in. I want people to feel free to be able to follow along at every step and be able to run things for yourself. And then I want to be able to provide you with a call to action so that you can be inspired, do something, move forward from this and contribute to this open source package. I think it'd be really fun. And I'll give you a schedule, which invariably I will break. I will not get to follow the schedule. We'll see how it goes. Now, first of all, appreciation and thank you to everybody for joining in. Just awesome. Welcome, everyone. I looked recently and I saw about 480 something participants signed up in this session. The more the merrier. This is exciting. Thank you very much. Specifically, Matt Hall, Brendan Hall. Actually, Brendan helping out a lot here with all the technical details behind the scene and all of Software Underground. What an amazing event. Thank you so much for all of the support that you're providing to facilitate this venue and to help us be able to work with our geoscience community using digital technologies. Now, fortunately, the tutorials will be recorded so you can come back to them later. And I'm actually looking forward to checking out Thomas Martin's tutorial, which is running at the same time as mine. I was thinking about just skipping out on this, but I figured there'd be some complaints about that. So let's make this interactive. So Brendan and I will be monitoring the Slack channel. And so this is the channel right here. During and after the event, we'll be happy to answer or continue the discussion at any point. So we want to be able to address any questions that may come up. All of the course content that I will cover right now, and I mentioned I want everyone to be able to follow along, are available to you on my GitHub account, Geostats Guy, and I have a bunch of repositories. And one of those repositories is GeostatsPy Intro Course. Please go ahead and grab that. Download it all. If you're new to GitHub, you just have to push this button right here, download it as a zip. The simplest thing to do is to just put it locally on your machine. You'll be able to launch the slides are in these lectures right here, and they are all in PDF for you. There's a couple of data sets that you'll need access to from the workflows, and all of the workflows available to you in IPYNB files. So there are IPython or Jupyter Notebook files for you to be able to run everything along. There is a little bit more information here about getting set up, but I'll mention those issues or those topics in a little bit. Easiest thing to do, go ahead, download that entire repository, put it on your drive. You'll have all the content that I'm using here, and join the Slack channel. If you have any questions or comments, I'll try to remember to monitor. Even now I'm going back to the Slack channel. And so I've just noticed some great comments on the Slack channel. So please go ahead and join the dialogue. This is a lot of fun. Now, what's my motivation? Well, I'm always super stoked about education and sharing knowledge among our community. We are all facing together a digital transformation. And we're not alone. We're all together. Every sector of our economy is facing this. New computing power, new computing resources, new methodologies, more technology to make us better at working with the subsurface. Engineers do more engineering. Geoscientists will do more geoscience. I'm really excited about it. And as part of this is this open source movement. More and more code available to help people to be able to get the job done. Now, I want to promote the use of GeostatsPy. I'm all about solutions. I don't really care if it's GeostatsPy or what it is, but I want open source solutions to spatial data analytics. And I'll talk a little bit more about that shortly. So I want to enable spatial data analytics and geostatistics in Python workflows. Now, GeostatsPy, the actual package I work to develop with some other co-authors, It's all based on the geostatistical library. In fact, I want to give very strong acknowledgement to Clayton Deutsch, Andre Journal for their original geostatistics package, which has been widely used throughout the world. In fact, the second edition of their book, the user's guide, is available in PDF now free of charge. Clayton Deutsch, my PhD advisor, actually has this available, and anyone can go ahead and look through the guide. It's wonderful. It's very accessible. GeoSlide was made widely available back in the 90s with the first edition, late 90s with the second edition, and was broadly adopted in the community and brought geostatistics tools to any interested practitioner to be able to get the job done. Now, with that introduction and motivation, let me just very quickly talk about who I am. And I hope that's okay, just to give a couple of statements here. First of all, if this is the first time you've met me, well, howdy, it's nice to meet you. My name is Pyrcz, P-Y-R-C-Z. It's pronounced Pyrcz. If you say it just like Pyrcz, then you're doing as well as we are. In fact, I think my family's kind of lost the ability to pronounce the name. We spent about 100 years in Canada after immigrating from the Ukraine. I'm new to academia. In fact, I just started in academia in 2017. In fact, I feel more like an industry person. I spent about 17 years, depends what you count, consulting, teaching, industrial R&D, and statistical modeling, reservoir modeling, uncertainty characterization, spatial data analytics, and so forth. And so I learned how to get the job done in Chevron's energy technology company, working with world-class data sets all over the world. And I left because I love to teach, and I thought I had an opportunity to give back, to share something I know. I've often said this. I said, I have no idea where I'm going to retire. Academia is more kind of a recent challenge, a chance to give back. There's a good chance I'll be back in industry one day. So I'll be back with you guys. I really do enjoy, though, teaching, and it's a great opportunity to share. I have expertise in this field. I shouldn't say anything as haughty as I wrote the book, but I kind of wrote the book in geostatistics, at least. Now, if I could actually go back in time and rename that book, I wouldn't call it geostatistical reservoir modeling. I would change it to spatial data analytics and geostatistics for subsurface modeling, or something more general. We didn't know at the time, right? Hindsight's 2020. But I have expertise in this area. I work in this. I judge this work. I review this work. I consult all over the world in this. And in fact, I even teach in industry. I taught 20 times in industry last year. And I'm sounding kind of braggy, sorry. But what I'm saying is that I'm constantly involved in our industry and in touch with what's going on as far as the practice goes. Okay. I'm also active in outreach. I promise, I think this is the last slide of bragging, but I'm active in outreach, social media, professional organizations. In fact, if anybody's on Twitter, I'm on Twitter. I'm the Geostats guy on Twitter. And what I promise, I share daily information about spatial data analytics and subsurface machine learning and so forth. I also have my YouTube channel that I will point to a couple of times, and I'm guest editor, something kind of more recent, a guest editor on the AAPG Bulletin special issue on subsurface data analytics and machine learning. In other words, if you got some cool work, contact me. We're looking for some really good papers to include. Deadline for submissions in the fall, so you still got time, okay? All right. Let me just introduce you to GeostatsPy right now. Now, I am making an effort to check the Slack channel, and I see that everything looks like it's working. Let us know if you're having any issues with following along with us, please. Okay. Good. All right. We just got the message. We're looking good from Denver. Thank you very much, Matthew. That's awesome. I love to hear that. All right. So what's the origins of GeostatsPy? And this is where I get my guitar down from the wall and start to play you a little country tune and tell you a sad story. Because this is my sad story. In the spring 2019, I taught a subsurface data analytics and geostatistics course. 1/3 of the course was geoscience students. 2/3 of the course were engineering students. I wanted a mixed integrated course, and I was really excited about that. Things are looking good from Brazil. Thank you very much, Marco. That's awesome to hear. It was an ambitious plan. What I planned to do was have a semester-long simulation exercise. I, the instructor, was going to be a subsurface manager. Each student was a member of my subsurface asset team. I was going to run it like we were in industry. Students were going to learn and apply spatial data analytics, with each of them having a unique data set. And they were going to provide me, their manager, with written presentations, written reports, presentations, so that I could track their progress as we went along. All good from Stockholm. Hey, welcome. Very nice. Very cool. Now, I was excited about this. And the class was really, there was some buzz around it. The class filled up quickly. I got a new room. It filled up immediately. There was 50 students, and winter break, I was putting the final touches on the course. I had all the content. What I needed was I needed some tools and example workflows to guide the students so they could get the job done. So first of all, I thought about using GS Live directly in Fortran. Now I got to tell you, I tried that the year before, or 2017, I should say. I lost 50% of the students in the first 2 weeks. They looked at the parameter files, they looked at the Fortran code, and they said, we cannot do this. Then I started to say, well, okay, I'll do Python executing GS Live executables using kind of wrappers. And the idea was you'd spit out or write out a par file, use just OS package to be able to run commands in the command window, and then load the output back into your workflow. It was not a great idea, but it was one way to be able to interact with GS Live and get the reliability of GS Live. It was an ugly solution, and there was tons of issues with it. I had to find a new solution. Now, let me just say, because I did say GS Live was an ugly solution, I got to pay a little homage here. I got to give a little respect now. GS Live, Geostatistical Library, here's the book cover right here. Here's an example of a parameter file. Open source geostatistics that made spatial modeling accessible to the world. In fact, many times I've dug into the guts of different applications in geostatistics, and I can see the spirit and soul of GS Live still in there. The work of Deutsch and Journal continues on all over the place, even till today. Parameter files, executables, outputs, visualization tools, everything was vector-based graphics and PostScript. It was kind of cool. As a PhD student, we would dig in and edit the graphics, make things look really cool. That was nice. It's all written in Fortran, so we all became experts in Fortran working with it. Great documentation with GS Live users. The user guide is great. Download it, check it out. Simple building block function-based approach. You have the fundamental steps in geostatistics. There's a function to do that, a function to do that, and you had complete flexibility to design your workflow to move through all that functionality. Anything could feed into anything else. You could create very complicated workflows for sure. Included all kinds of foundational functions, easy to modify and extend, and so a lot of people have done that, modified the code. Much of GeostatsPy is a translation re-implementation of GS Live. I want to give full credit right now for that, for their original work. Now, I considered a variety of options to be able to do geostatistics. And so I like the work of Edzer and GStat over in R. I'm a fan of R. I started out in R, and R is great. Great contribution, but I found it to be somewhat impractical beyond the univariate simulation. And it was not currently under development. There was no current work on it. PyGeostats looked really good from CCG, my original school, up there working with Clayton Deutsch and his consortium. The only problem, it wasn't available to everyone outside of the consortium. And so I was unable to use it in my class. I tested a variety of open source Python packages, and I want to give full credit. I know there's a variety of efforts going on. Some were not currently maintained up to date. Some lacked documentation and examples. Some just didn't run. Some had bugs and issues. I literally started down the path of using another package, an open source package, and that morning of a lecture had some type of update in NumPy or something, broke the package, and I was stuck in front of a class of 80 students. And so I promised myself never again. I needed something that was reliable, robust. It had to work. It had to be flexible for what we need to do. So what did I do? Well, as most professors do, I spent all my weekends for that term re-implementing GS Live in Python just days before the lectures. Under this pressure, I decided to make some limitations. Two-dimensional only. I removed some advanced options, and you'll see there's some limitations. Now, I hope it was okay. I kind of told the story of GeostatPy. I hope what you can hear from it, though, was the overall spirit was this idea of being able to provide an educational tool to support learning in my classes and elsewhere around the world. And so that's my motivation overall. Now, how is GeostatsPy structured? There's two major modules within GeostatsPy. And some of that's legacy. I'd probably change it if I could now. I should probably. The GSLib module, so geostatspy.gslib, is a re-implementation of the data visualization. Import, export Python GSLib, moving between GSLib formats and Python, and then those wrappers, those ugly wrappers for being able to move into the Fortran executables from your Python workflow. The geostats module, that's where I got brave. And I said, let's just go ahead and re-implement GSLib subroutines and all of the functionality. And that's what was done. So all of the fundamental building block subroutines were re-implemented, along with re-implementation of the major algorithms for geostatistics in 2D. So that's the overall structure. Let me talk about each of them just to give a little bit of motivation. You know, spoiler alert, I'm going to invite people to actually participate in the package. I should explain the structure. The re-implementation of data visualization with Matplotlib, the idea was that in GSLib, one thing they did very well is they canned up some of those common visualizations in the subsurface, location maps, pixel plots for exhaustive gridded data, the histograms and so forth, into very nice, simple visualizations that were common. People like that. And so we re-implemented all of those kind of location map pixel plots like this one right here with simple inputs. Spoiler alert, it's just Matplotlib under the hood. But the point is, it was a bridge for new users who were unfamiliar and could make a transition from GSLib directly to GeostatsPy and Python, having all those same visualizations. Another thing is we had the import export Python GSLib type functionality. It turns out that a lot of people still want to be able to access that really good code in GSLib. It is so well tested. It is so efficient. I still say some of that Fortran, is still blazing fast. It's very efficient in memory and speed. And so I want to provide the options to be able to go out of Jupyter, go out of Python, use GSLib and come back. So there's a variety of import export functionality to go between GSLib file formats and the standard Python classes we work with, like data frames and ND arrays from NumPy. So GSLib uses GeoDAS ASCII format. So there's functionality to move back and forth. And here's an example code right there. Now, the final thing in the GSLib module were wrappers to the GSLib executables. And please don't laugh at me. This is exactly what I'm talking about. Imagine a function that would take your data set, your secondary data, output it in GSLib format as an exhaustive array of values mapped over space, put the parameters in from a dialog within Python, build the parameter file like the GSLib program, save it out, and then just run it. Get the output, load it back in. That's literally what I mean. And I know when I use the term wrapper, I should always go wrapper because I know that's not a proper program as far as wrappers go. But it was a fast solution to be able to get the job done. Now, if any of you are working with a Mac, I've had some say, well, GSLib, if you go to geostatlib.com, you can find all the executables in Linux, you can find them on Windows, but they don't have them in Mac. And one of my students, actually Wendy Liu, has actually compiled all of GSLib and put it, and we have it available on GitHub if anybody wants to ever run those executables on the Mac OS, which is great. You'd be surprised how many students are using Macs. All right. So Geostat module is re-implementation of the fundamental building blocks, the subroutines. Now, I give full credit to GSLib again, because it turns out some of those subroutines are really good, they're robust, and they're very fast and efficient. Distribution transformations are really good, spatial covariance calculations, geometric distances, working with entropy in space. They do a fantastic job at all of that. Rotations, which invariably you have to deal with flattening and rotations within your geomodeling and Kriging solutions, and working with different distributions, cumulative distribution functions, interpolation, extrapolation. All of those basic building blocks, which I find to be very robust, I re-implemented them according to the original GSLib code. And then the geostatistics, what I would call the major functions, the major algorithms that we all need to use. Examples of those algorithms, and those are all re-implemented here in 2D, declustering. That's very fundamental. I don't know if you all recognize this, but I tell my students, all of our spatial data, our sparsely sampled spatial data, is biased. It really is most of the time. Anyway, I'm on a soapbox again. I'll stop. Simple ordinary Kriging, sequential Gaussian simulation, indicator simulation methods, the co-located co-Kriging and simulation approaches, a wide variety of geostatistical algorithms. The workhorses of geostatistics are all available in 2D in GeostatsPy. Okay, now once again, I want to give appreciation to the contributors. Some of my PhD students like Hong Gong and Wendy. Other people, Anton was really great. I met him during some teaching over in Ecuador, I believe, and he jumped in and just started doing great things. It's all available on GitHub. I welcome anyone with pull requests, making edits and improvements. Please go ahead and jump in. I would love to see this expand. Now, let me start with the positives. What's good with GeostatsPy right now? Well, it's available on PyPy, so anyone in the world can get access to it. Someone made a comment about me soapboxing in my tutorial. So I'll try to calm it down if you have any issues with soapboxing. Of course, you know, as a professor, that's part of my job is to kind of lecture. You know what I mean? Like lecture time. Okay, GeostatsPy is available on PyPy repository. I know it should also be on Conda and all of that too. It is, I should also say that the documentation ain't bad. There's a bunch of documentation on the GitHub repository. There's some effort to do doc strings and so forth. It is not so bad. The thing where I think GeostatPy is really rocking, doing very well, is in the area of well-documented example workflows. I have many, many workflows for all the variety of major steps that we need to take in geostatistics, common with realistic data sets, with some expert kind of suggestions and help, well-documented Jupyter notebooks. And I think that's really good. There's many, many of them, and I use them to teach all the time. So check out my GitHub account, my Python numerical demos, they're all there. The other thing I think that's kind of very cool, and I'm going to show this off today, is interactive demonstrations that are supported by GeostatsPy. A wonderful teaching tool. What I always say is the best way to learn data analytics and machine learning is to play. Play with the tools, play with the algorithms, experiential learning, see how they respond, break it. I'm a big fan of Mythbusters. If it doesn't blow up, just add the load, make it stress it even more. See when the system breaks. That's the best way for us to learn and understand. All right, I want to say right now, thank you to all of you who are interacting during this discussion. I appreciate it very much, and I encourage it as we go along. What I would say if this was a typical Zoom meeting, even if there were 60 of you, unmute at any time, just go ahead and speak up because I really do like interactivity. It's much more fun that way. Okay, now what needs work? That was the positive message. Now that I've kind of like made it sound great, well, the doc strings documentation could be done much better. It could be greatly improved. There's a lot, and this is a problem in many open source applications. Opportunities to improve docs are always there. I think that there's great opportunities to expand the spatial data analytics, spatial statistics. Recently, I was doing some work in mutual information. Super cool. Ripley K functions for understanding spatial point processes. Workflows that assist us with this type of spatial statistics and other types of more expanded statistics can be very helpful to us. Efficiency optimization. Oh boy, I know. I haven't done a great job here. I used a little bit of Numba for pre-compile acceleration. There's much more that can be done to speed it up, and support for full three-dimensional workflows. All right. The plan. What are we going to do right now? Because I've got about, I've got about 2.5 more hours of your time, I guess. So let's go ahead and lay out what we're going to do. We're going to demonstrate GeostatsPy for spatial data analytics and geostatistics. We're going to start from zero. I'm going to assume you know nothing about geostatistics, which means I'll cover just a couple of slides to get you understanding a geostatistical concept, and then I'll get you to use GeostatPy and do it. Then we'll walk through in an interactive manner. Then we're going to walk through all of the steps to a more robust workflow, and then we'll go to the next topic. We'll do calculating variograms, in other words, quantifying spatial continuity. We're going to model variograms, in other words, building a model of spatial continuity for estimation with uncertainty. And we're going to build estimation models in space. Okay, so we'll do all of those things. Hey, howdy. Vivian, thank you very much for saying howdy. Nice to see you. And also someone just joined from Houston. Arham, hey, nice to see you. Okay, so we're going to work with a two-dimensional synthetic subsurface data set for each one of those. That's the plan. Now, how are we going to do that in just 3 hours, 2.5 hours now? Well, we're going to rapidly cover the basic concepts with a couple of slides. I cannot teach you geostatistics, neither can I teach you Python in the time that we have together. We could spend more time together. That'd be fun. So we'll rapidly cover it. Let's just have that attitude of let's play, let's try things out, let's see how it reacts, and let's see the value of having in Python geostatistics available to us, spatial data analytics. For those interested in deeper knowledge and more details, guess what? I have all of my lectures. In fact, as a professor, I committed to put every single one of my lectures from 3 separate courses. Hey, thank you very much. I want to recognize that Matt Hall has just spoken up on the Slack channel. If anybody is concerned about the rate or the speed at which we're going here, at any moment you could, afterwards you could rewind and go through, you could rewind and you could pause, you could do, you can kind of go through at your own pace. Okay. I'll try to, now I always tell my students, if there is ever a mutiny and everybody starts to speak up and say, come on, Pyrcz, we can't follow this. This is not helping us. Please jump in. Let's have that mutiny. You guys can make me walk the plank and it's fine. And I will just absolutely slow it down. This is all teaching focused, not schedule driven. Okay. If you want to go down that journey to become more of an expert in this field, I have recorded every one of my lectures and I've committed to keep doing that. All of them are available to anyone in the world on YouTube. And my attitude is that education, we need to make it available to lift our entire community. Okay, now I had a question if I'm going to cover heteroscedasticity, and I got to tell you what, I will say it at least once because that is kind of like eating my vegetables. Every day I've got to at least say heteroscedasticity at least once. So thank you very much for bringing it up. I appreciate that. Okay, so how are we going to do this in 3 hours? We're going to have interactive demonstrations where you can turn the dials. You can interact with dashboards with the geostatistics, variogram calculation, variogram fitting, and Kriging. And that'll give you a chance to see how the tool performs, and it's pretty efficient. You'll see how well it works in real time. Then, we'll play around with it. We will walk through much better, more thorough, well-documented workflows where we'll go step by step. We'll walk through that so you'll see the flexible building block approach to GeostatsPy. And that's intentional. You'll see that was a very fundamental thing about GeoSlide, to make it very simple function building blocks to build any workflow with very little kind of constraint. It was very free and flexible. Hey, Arham, thank you very much for the compliment on the YouTube videos. I do appreciate those people who are checking those out. I do always welcome feedback. Errata and so forth are very much appreciated. I try to improve them. Okay, so calibrating our goal today, goal is showcase GeostatsPy, not to teach spatial data analytics. If you have no knowledge here, you'll get some new ideas. Check out my YouTube lectures for greater depth. All demos, data sets, and workflows and more are available on GitHub. And so anyone can try things out and expand this. All right, let's talk about getting started. I have been told by the powers that be, Matt and Brendan, that really everybody should have Anaconda installed at this moment. Okay, I'm not hearing anything. The virtual world has not reacted in a shock or anything, so I'm going to guess that's true. What I need you to do, if you want to follow along here today, is you need to install GeostatsPy, my geostatistics Python package. Not a big deal. Now, everyone's already installed Anaconda. I didn't see kind of astonishment when I made that statement. The easiest way to install GeostatsPy, if you have not done it yet, is to go into Anaconda. If you're in Windows, just type NAV in the search, and you'll find Anaconda Navigator. Let it open up. It'll open up. It takes a little while. It's got a cool symbol that comes across your screen. Open it up. And what you'll have is a dialog where you can select environments. Right beside base, you can go ahead and select this arrow. And under the arrow, you can say open a terminal. If you open that terminal, you can type pip install GeostatsPy. Now, why do I tell students to do it this way? I've had students just open up a command terminal, install GeostatPy, and then they open Jupyter notebooks and they can't find GeostatPy. This is the one way I can just guarantee for a beginner that you'll find it. It should be where it should be, and then you'll be okay. Okay, so go ahead. Thank you very much. So we have a comment here on the Slack channel. Go ahead and ask questions, and we have some of our expert assistants. I appreciate very much. NTBZA with the South Africa flag. Thank you so much for your offer of assistance, and anyone else who wants to help out with anyone who's having any issues. We will have a little bit of content at this moment where I'll talk about an introduction to variogram calculation. So you'll have a little time behind the scenes that kind of gets set up if you're struggling. Okay, thank you. I do appreciate it. This is the great thing about the software underground community. We don't stand alone. Everybody's here assisting each other. Well, anytime you do anything, there's got to be a call to action. We're all trying to improve and learn and do something. I invite contribution to this package. Documents, optimization, coding standards, all of this is super cool. Code readability, testing, examples, expansion. There's so many good things that can be done to improve the quality of this code. It is a skeleton, bones that really do need a lot more meat on those bones. Now here's the schedule. This is what I plan. If you look, I'm 10 minutes behind schedule, but that's pretty good for me. I think I'm doing okay. Anyway, this is rough. This is the introduction setup. We'll do variogram calculation up until just past 2 o'clock. We'll do variogram modeling during the next hour or so. We'll do Kriging, and then we'll go ahead and we'll finish up with conclusions. And we finish up at 4 o'clock, I believe, right? Okay, good. So that's the plan, that's the schedule. And now I'll tell you what, that right now, I bet you after half an hour of listening to me, there's some of you who are thinking, man, when do I get to take a break? This is getting to be too much. Don't worry, we'll go through this and you're gonna see right after the interactivity or during the interactivity parts, I will ask you to spend 5 minutes or so trying things out on your own, doing things. That would be a natural time. That'd be a very natural time for you to be able to take a break and you wouldn't miss anything. Now, Matthew, I appreciate that. You're ahead of your Gusso talk. Are you saying I was running behind schedule at that talk? All right, so let's go ahead and let's go to the next content here that I want to cover. In the next slide deck we're going to open is the 01 variogram calculation. So I will have just a couple of slides to explain variogram calculation. Okay, let me put this in the presentation mode. All right. Oh, Pauline, is it right now 11 p.m. for you there in France? Thank you very much for showing up. And hey, howdy, Pauline. Nice to see you. Okay, so let's talk about variogram calculation. Let's do an interactive demonstration with GeostatsPy for variogram calculation, and then we'll do a more thorough workflow for variogram calculation. Now, I feel, as we would say in the fine state of Texas, that I am preaching to the choir if I was to say that spatial continuity has a significant impact on our models. I think there's many cases in which spatial continuity really does matter. In fact, for oil and gas, and I do a lot of work for oil and gas, hydrocarbon recovery, or even water, and so forth. I'm doing some work too with groundwater. This heterogeneity has an impact on flow rates and overall recovery from the subsurface. Often, as something kind of fun to do, I introduce this slide to my students, and I don't show this part. I just show this part up here. Let me go to a laser pointer. I show this part right here. And I ask the students, is it better to have a long-range spatial continuity or short-range spatial continuity? And I get the students to agree that is very short-range spatial continuity, and that's longer-range spatial continuity. And then I tell them, okay, now let's flow it. This is the time of flight with a time of flight type of approach to simulation. It's a very simple model, fast marching approach. We inject here, we produce from these four wells right here. And what you'll see is that with the completely heterogeneous model with no spatial continuity, we get a nice uniform replacement, a piston-like displacement, high recovery factor. We're doing a great job if we're treating contaminants and we're trying to do some type of pump and treat. That's great news for our contaminant remediation. Now, then I show them this model right here, where you can see clearly we're having troubles. And in fact, I show them more extreme models, spatial continuity matters, which means we need to model spatial continuity and we need to put it into our models. That's a lot of what geostatistics is all about. Now, as we go through this, if you're disappointed, because I'm going to literally have 3 slides talking about variogram calculation, and you say, come on, Pyrcz, there must be much more than that. Please go back and check out my recorded lectures. I, in fact, have more lectures than this on all of the aspects of spatial temporal stationarity. You know, part of my job is to actually give you terms that sound cool at dinner parties. I think that's useful to all of us, right? Please promise me you'll use that at a dinner party. Variogram introduction, spatial continuity measures, and variogram calculation, the details. I have a whole bunch of lectures on that. So there's more if you want to get into more details. Variogram calculation. This is the equation right here. And some of you have seen this before. The variogram is simply, if we ignore the 2, this is just an average of the square difference of values separated by a lag vector h from tail to head, and it's averaged, which means spatially we calculate that average square difference at different locations that have that same relative lag vector, the same direction and distance. That's the whole idea of a variogram. The 1/2 is why we call it a semi-variogram. We don't have time to get into that today, but let's just call it a variogram, and we'll talk about variogram modeling. So now what we need to do is we need to take that and calculate the difference between a value here, tail location, and head location here, square it, difference squared, difference squared, difference squared, get the average of that, 1/2 that, and we plot it. And if you do that for 200 meters, if this lag was 200 meters, I would get a point on my variogram plot. An experimental variogram plot is what we'd call it in the business. Now I could repeat that by changing the length of the h lag vector, and I would get multiple points, experimental points, and I could plot them up like this. Now I have a function that I can explore. It is a measure of Euclidean distance versus difference. I like to say geologic distance, because really often in geology, we judge kind of the change in time, distance in geology, by differences. The sedimentary system changing, eustatic rise and fall, sequence stratigraphy, and so forth are all kind of about this idea of differences in the sedimentation. Okay, so this is really exciting because now we have an experimental function that's telling us about multi-scale degree of dissimilarity or change. Now, let me make a couple observations. In my lectures, I make like 6 observations. Here, I'm just going to make a couple observations. Can I convince you that as the h vector separating the tail and the head increases, that the amount of variability you observe, the average square difference, will probably go up on average? Now let's look at this exhaustive data set right here and take your fingers, put them up to the screen very close to each other and scan through and make comparisons. And what you'll find is a very short distance, you compare low to low. Purple, the cold colors are low values. This could be a porosity field. The red hot colors are high values, just for reference. If you go very close with your fingers at a short h lag vector, you're comparing low to low, high to high, medium to medium. You don't see a lot of difference. So you expect the points to be close to the origin here, a very low number for the semi-variogram. As you increase the width of your fingers, a longer h lag vector, you would expect that you start to see greater dissimilarity. And so that in general results in, not guaranteed, but in general, a monotonic increase in the variogram value with distance. There's a lot more devilish details, but I'm not going to cover those today. Observation number 4, you must plot the sill to be able to interpret a variogram. What is the sill? The sill is just simply equal to the variance of the feature, the spatial feature of interest. Now here, this is very powerful. We can now make a lot of interpretations. The first thing is the variogram, if it's stationary, and that's a detail we aren't going to get too much into right now, but we would expect that it will rise up and reach the sill and level off. The point you reach the sill is known in geostatistics as the range. This is the point at which you have no spatial continuity. In fact, what I tell my students, if your boss ever comes in your office and tells you, make a prediction pre-drill away from an existing well beyond the range, you have my permission to tell your boss you know nothing. Now, I know there might be geologic secondary information and trends and so forth, but it's still fun to say, isn't it? And so we just recognize the fact that beyond the range, we no longer have spatial correlation. In fact, a point experimental variogram at the sill, if you plotted all the head and tail values, that scatter plot would be like a shotgun with no correlation. You can interpret it like that. Okay, so we need to plot the sill and the concept of the range. We're going to use the range as a parameter to constrain our variogram models too. So you'll see that shortly. Now, it turns out the world is not a simple, happy place. The world is full of complexity. We don't sample the subsurface with regularly spaced data. We're going to have irregularly spaced sparse data. So when I said we'll calculate the variogram and we'll take tail and head and we'll move around our data space looking for pairs, if you did that, you would only find maybe one pair and no more. Because what's the chance of data and space being exactly 500 meters apart at an azimuth of 0.90? It's not going to happen. Like down to 500.000, azimuth 90.000. At that precision, you'll never have data paired up. And so we have to make a choice to kind of blur our vision a little bit, squint and blur, and say we're going to accept a little bit of tolerance. We'll accept tolerance if I want to make comparisons between a tail location here and a head location right here at this many meters at that direction. I'm going to say I'm going to accept a tolerance in the lag distance and a tolerance from here to here. That's the lag distance tolerance from here to here and from here to here symmetrically. So I now have a bin along that vector. And I'm going to accept a tolerance in the angle resulting in this shape right here. And now I can actually find pairs. This would be my template right here. 1, 2, 3, fourth lag bin. Maybe that's 400 meters. And at that direction, now I have a template. I can actually take that template if I wanted to, and I can actually just put it on the data locations and look for all possible pairs. And guess what? If I put it here, I found those two pairs. You see that? And I can go here and here and here. And if I move it around to every possible location, to every possible data location, these are the pairs that are 400 meters apart, plus or minus 50 meters with an azimuth of 0.45 plus or minus 20 degrees or something like that. That's what we have to do to calculate the variogram. Now, there's an issue here. Well, how big of a tolerance should you use in distance and azimuth? Now, it turns out it's the same problem as histogram plotting. Have you ever made a histogram and used very big bins and you smooth all the information? Or use a histogram, use very small bins, and then it becomes very noisy? It's a balancing act between too much noise and too much smoothing to get the most interpretable results. That's the best I can do for you right now on that. Okay, let's do an interactive demo. I talk way too long. I apologize. Let's go ahead and look at GeostatsPy. So what I want to welcome you to do, and this is going to be our first one that we open up together. If you go to the original files, you're going to open up in the workflows, we have interactive variogram calculation. All right, Arham, thank you very much for that feedback. I hope the introduction was useful to people. So I think it's good if we're going to play with code that we do understand what we're doing, right? Interactive variogram calculation, that's what you're going to want to open up. Now you can open up Jupyter Notebook and just load that up. Or if you've installed the package that allows you to, you can just double click that and it'll open up Jupyter for you. You can have that set up. Either or, what will happen is you'll end up, let me see which one is it. Here it is. And I'll go ahead and go up to the top. If you get this opened up, hey, Alistair, thank you very much for the feedback. I agree. I think the interactive variogram is actually really fun. I actually was playing around with it and I put a little thing on Twitter about it. I got a little hypnotized. It's a great way to communicate the idea of spatial continuity, I think. Okay, so thank you very much for that. I appreciate it. So let's go ahead and look at this interactive variogram calculation demonstration. All right, thank you for that, Marco. So I'll zoom in. Are you guys able to read that font? Is that clear for everybody? I want to make sure it's viewable. Every time I make one of these Jupyter notebooks, and I'm not going to spend time introducing and talking about Jupyter notebooks. It's kind of like Anaconda. I'm going to have to just assume that people have already done some basics in Jupyter in case there is somebody stuck. Remember the run button. That's how you run something. And remember the stop button in case you're stuck. Now, what you'll need to do is click on this first box and let's run as we go along. As I tell my students, if you open up a Jupyter notebook, until you've run a block of code, it actually hasn't happened. So you do need to run all of this code. The first block here after my initial introduction is the importing of GeostatsPy, GeoSlib, those utilities, wrappers, and the visualization reimplementation, and Geostats, the hardcore reimplementation of the functionality and methodologies. Thank you very much for the feedback, guys. It sounds like, okay, I have a request to make the font a little bit larger. How's that? Is that good? Okay, let me know if that's not large enough, guys. Remember, I want to make sure everybody can follow along. All right, so let's go ahead and import my package. So if you're wondering whether or not you installed GeostatPy correctly, if you ran this command and did not get an issue, I tell my students, no news is good news. Then it means that you have this now available. Now we're going to use a bunch of, I love NumPy, I love pandas, NumPy for gridded data and arrays, pandas for data frames. And we're also going to use OS so we can set a current working directory. I like to do that. I'm old fashioned. You could use intake or other more modern data engineering approaches, and matplotlib for plotting, and IPyWidgets. All of this interactive workflow is IPyWidgets using matplotlib and the code from GeostatPy. Okay, let's go ahead and import that. Good to hear the font's a good size for you. Now, please set this equal to your current working directory. So wherever you put the data files, make that your current working directories. Now, I just copied them to a course folder right on my D drive on the local hard drive. I'm very simple that way. And go ahead, you'll have the data files that were available to you. They're available in the data. Go ahead and make sure that those are available to you, and you should be able to then load them up. So let's go ahead and we'll run that. We'll change the working directory to whatever directory that you put the data files in, and we can import the data files. Okay, if you've done that, now we're good to go. Now, I'm going to do a non-faces based approach. If you want to separate the data frame that we loaded in and we just previewed into by faces, go ahead, include this code, and you could work by faces. I'm doing sand shelled porosity mixed together. There's a lot you could do with this data set. Now let's go ahead and look at the summary statistics of the data set. I love that. Data frames are really cool. You load the data in as a data frame. You can describe summary statistics. We can see if there's any issues. We can do histograms and so forth. Now, and thank you very much for comments around the slashes that you're using. It may depend on the convention you're working with as far as // // and I think Macintoshes are a bit different and so forth. So thank you very much for everybody helping out there. Okay, so we're going to do a normal score transform of the data. That's one thing you can do in GeostatPy. It's actually a very good normal score transform. It's very robust. We'll do that on the porosity and permeability data. We're only going to demonstrate calculation of variogram on the porosity data. Then we can preview the data frame. And yes, we have normal score transform porosity right here for us. So you can see that spanning between about -3 to +3, standard normal, mean of 0, variance of 1. We do this because for geostatistics for sequential Gaussian simulation, you need to do the normal score transformation for theory. And I'm assuming eventually we want to take our variogram to simulation. Okay, so let's go ahead and do some data visualization. We want to check and make sure the transformation went well. Well, you got to fall in love with that. That's awesome. Original raw porosity right here, the CDF. Hey, let me ask anybody by chat window, given this CDF, what shape of distribution is this? The original data. What does it closely approximate? I'm going to carry on, but let me see in the Slack. I wish if I had chocolate bars, I'd be like throwing them out to the class or something like that. Okay. Now, then we do the transformation right here. And for extra marks, what shape of distribution is the permeability? And here's the transformation here. So you can see where we got in the end. Okay, so distribution 1, distribution 2. I'm still waiting on the Slack channel. Nobody's answered so far. Okay, let's go ahead and let's inspect the data. Remember that geostatistics and variogram calculation is fundamentally a spatial process. You need to look at the data. You need to evaluate it. Yes, the first one, Matthew, is near normal. It's almost normal. How about the second one? Extra marks for that. They're both cumulative, but one of them is not normal. The other one is something else, and you can look back at it, right? Okay, so we have all facies, normal score, porosity, the standard normal porosity. Log normal, yes, you nailed it. Yes, normal and log normal. It's important to be able to look at a CDF cumulative distribution, be able to evaluate it. And you can see it. It has that. Yep, you nailed it. You nailed it. Got it. It's normal and log normal. Okay, so we have the n-score porosity, n-score permeability. Why do we visualize data when we're doing a variogram calculation? What am I looking for here? If I have to determine a lag distance, a minimum lag distance that I'm going to be looking at the data, I want to see what's the closest data spacing. If I want to calculate a directional variogram, I'm actually looking for directionality. Now, looking at this data set right here, everyone can see it, normal score transform of porosity, a rank preserving transform. What is the directionality in this data set? Remember, 0 azimuth is north-south in the y direction. 90-degree azimuth is in the x direction. What is the primary direction of continuity? Which direction has the most amount of continuity here? What do you think? Anybody? Okay, I'm going to leave that question hang. I want to see if somebody gives me the azimuth, because looking at the data, you can often see minimum data spacing and the directionality. I hope you can see it too. We also look at permeability. Permeability tends to be a little bit more noisy. And then we'll go ahead and look at normal score permeability versus porosity. Why do we do that? Because porosity is often easier to model. And if there's a pretty reasonable relationship between the two, then it tells me that information I learn about porosity, spatial continuity, can be used for the purpose of understanding what's going on with permeability. They can support each other through their correlation. If they're correlated closely, they have similar. All right, look at this. We got 4 people speaking up. I'm hearing a pretty strong response of 045. I probably have that backwards. I always mix it up, but you know what I mean in this direction right here. Yep, you can see the directionality. Keep that in mind. It's going to help us do the variogram calculation. Thank you very much to all who are responding right now. All right, so let's do experimental variograms. The parameters we have to choose are the minimum, are going to be the lag distance, that unit lag distance, and then the tolerance on the lag distance. Often we default to 1/2 the lag distance. The number of lags, we generally calculate a variogram up to about 1/2 the extent of the data set, which is reliable. The number of pairs will drop off after that. The bandwidth, I didn't talk too much about bandwidth. We won't focus on that. The azimuth and the azimuth tolerance. Okay, let's go ahead and calculate some variograms. Okay, so what's going to happen now is all we've done here, and I won't explain it, is we set up our dashboard. We set up a function that uses GeostatsPy to do the variogram calculation. Now let's instantiate our template, our dashboard. Okay, I hope everybody has this. And I agree, Matthew, thank you very much for that comment. Porosity is much more directly measured and more reliable. We often have many more measures of it. We can get a pretty good grapple of it from a variety of different well logs, while permeability is much more tricky. I do agree with that. Thank you so much for your statement there, Matthew. Subject matter expertise matters a lot when it comes to spatial data analytics. Okay, go ahead and make a small modification. Just make any modification on this dashboard, and what will happen is a variogram will appear. Okay, so what do I want you to do with the variograms right now? And so I had some ideas right here. Okay, so this is your mission. I want you to go ahead and do some variogram calculations. I'm going to walk through with you, but I thought, first of all, I'll let you try some stuff out. Start with a lag distance of the minimum data spacing. Go look at the data, figure out the minimum spacing used as a lag distance. Start with a lag tolerance of 1/2 that lag distance. Start isotropic, in other words, set the azimuth tolerance to 90 degrees, and then go ahead, play around. Try to get a good isotropic variogram, then start to narrow up the variogram azimuth tolerance, and then you can start to figure out if there's a directionality. For the directionality, look at the direction with the greatest amount of spatial continuity, in other words, the longer range. Now, I'll give you a hint here. Very long range is one where you never get to the sill, and I think you're going to see that in the data set. All right. Now, I see, first of all, I see a couple of people with errors here. if you have the tmin error, you could, what that means is you downloaded the workflow maybe a while ago. I did fix that. One way you could do it is just, let me go back here, right here. And you could just right before, I think if you were to go right here and just type tmin equal, oh, do I have the function there? Negative 999.9. Just give it a default right there. I think that will fix it. Okay, see if that cleans it up for you. Now, if you're having problems with Numba, yeah, it sounds like your Numba's not properly installed. And thank you very much for all the experts jumping in. I do appreciate that. Now, Matthew, if you're absolutely stuck, you could just go directly to GitHub and do a quick re-download of the workflow and you'll be fine, because I did correct that error. I do apologize. I think I corrected it like mid last week. Okay. Okay, so remember, right now you're playing. And you remember when I said natural breaks and you can take a break anytime, this would be a time right now. Remember, start with a lag of the minimum data spacing, start with a lag tolerance of 1/2, start isotropic, and try to start narrowing the azimuth tolerance. Okay, good. Oh, good, Matthew. Thank you very much for the feedback. So when you downloaded the new one, it started to work for you, right? Okay. Hey, Nate, thank you very much for joining in, Nate. Yeah, check out the recording later on. Always happy to discuss, eh? Appreciate you joining. I'm going to give you 5 minutes and you can mute me and tell me you're going to take more time. Now, I always like simulating in the virtual world, the classroom, like as if I'm there with you, because I really do prefer that. So I'm going to sit here as if I'm at the front of the classroom, and you can call me over to your desk to say, hey, what about this? Here's an idea. Just throw something in the chat window. I'll respond to it. I'll hang out here. I'm curious, how many people do we have on YouTube? Awesome. Thank you for that, Matthew. Thank you very much. Hey, thanks a lot, guys. Two more minutes, and then I'm going to go into live demo mode and discuss. One more minute. All right, so let's get started again together. I hope that this worked for you. I think many people, it's been working for you. There's been some questions. I do appreciate experts who are jumping in to help each other. That's the community. That's an exciting thing about Software Underground. Now, let me ask you, help me model this variogram. What is the minimum data spacing, or what would be a reasonable distance that we can go apart and still see a lot of pairs? What do you think? This is 0, 1000, 0, 1000. The aspect ratio is a little messed up, but it's not bad. It's not too bad. What is the general distance between the data? How close can we go and be able to see and have enough pairs to calculate a statistic? Anybody have any suggestions in the window? And I already heard, it sounds like people are going to suggest about 0.45, 45 degree in this direction is going to be my major direction when we start to go directional. Okay, so I'll tell you what, I look at that data set and what I see is I see a lot of data like that, like that. I really feel like this is 200 meters, maybe around 50 meters is probably a good guess to get started at. We should get enough pairs to be able to work at. Okay, so let's go ahead. Let's set the lag to 50 meters. Now, do you notice how all my points shifted? The reason being is the number of lags is set. So what's happening is that we will see that if we go 50 meters as a unit lag distance and we only consider 10 of those, our furthest experimental variogram point is going to be 500 meters away. Okay. Now what we can do is we can increase our number of lags and we fill in the rest of the detail. Now, do you all see how the size of the circles are varying at the different distances? So at 200 meters, we have this size circle. At about 50 meters right here, we're seeing a very small circle. Those circles are scaled to be proportional to the number of pairs available. In other words, it's telling you about the reliability of the variogram. Okay, so now what we can do is we can calculate at first an isotropic variogram. So if we set the azimuth tolerance of 90 degrees, what will happen is we're actually calculating isotropically. So this is the variogram calculation going right through the center of all these big circles, lots of pairs, if we go isotropic. Now, how do we know we're isotropic? Look what happens if we change the azimuth. Nothing changes, because when you're isotropic, the azimuth is 90 degrees plus and minus, directionality doesn't matter anymore. Okay, so we can see that effect. Now, what would happen if we were to narrow the azimuth tolerance and make it very narrow? So we can make it, smaller and smaller and smaller. What will happen is we'll get fewer pairs and we get some result that's more specific to the distance offset. In fact, if your lag azimuth tolerance is too big, look what happens. The whole thing will become kind of smoothed out and you'll kind of not have as much information if we drew a line through the center of these circles, which are all very large, a little bit hard to see. Okay, so let's put the lag tolerance back at a small number. Okay, now we're going to do anisotropic or directional variograms. Let's decrease the azimuth tolerance to something on the order of maybe about 20. That would be very common. In Geostatistical Library, they defaulted at 22.5, half of 45 as an azimuth tolerance. Okay, so now we're looking in the angle of the Y direction. Now what we can do is we can click on that button and we can push up, push up, push up, and you can see what's happening. The range of spatial continuity at 0, 0, 0 azimuth is about 300 meters. At an azimuth of about 0.25, which now we're starting to rotate like that, we're starting to see the ranges increase to about 400, and that might even be a little bit because of error in that one point. Maybe the azimuth is more over here, 500, 600 meters. There's a little bit of noise in our data. If we wanted to, we could smooth it up by increasing the lag tolerance so we get a little bit smoother results for our interpretation. Okay, so we can go ahead and check different angles. Look what happens when we go to 45 degrees. Now, what was our direction, our major direction of continuity? The direction with the greatest spatial continuity was 0.45. Look at the degree of dissimilarity over distance. You have correlation. We have not even reached the sill at 1,000 meters. We have correlation beyond 1,000 meters. That clearly is a major direction. Now, what we could do is we can keep going and look what happens. It starts to come back up. And you can do this. And this is where I told you it gets a little bit hypnotic, because you can actually scan through all the azimuths and see how spatial continuity will vary as we move across those different directions, and we can interpret it. Now, for variogram modeling, what we're going to want to do, I don't know how much longer that's going to go on. What we want to do is we want to get the variogram in the major direction, we'll say 45 degrees. And we want to model 45 degrees, and then we want to take 90 degrees from it, which would be 135 degrees. And we want to model those two directions. They become, or they're orthogonal from each other. So we've got 45 here, and we got 135 going this direction here, the major direction, the minor direction, and we modeled both of those, and we assume a geometric anisotropy model to be able to interpolate between them. All right, what do you think? Are there any questions about this interactive demo for calculating a variogram? Anything on the, go ahead and throw something in the chat window if you'd like to. All right, how about this? Was this cool? Was this useful? To be able to calculate the variogram on the fly with a dashboard like this? I think it's a good teaching tool. Okay, so let's go ahead. What we'll do next is, if you go back to the files, you will find that there is under workflows, there is a GeostatsPy variogram calculation. This is a more robust and thorough workflow to support people so that you can learn from it. Okay. All right, Malcolm, thank you very much. It's cool. It's cool. I got it. It's cool. I do appreciate hearing back like that. I think it's also very useful to learn to be able to play with the system, i.e. in this system, a variogram calculation. Thank you very much for the feedback, y'all. Okay, so let's go ahead and we're going to open up these GeostatPy variogram calculation. We'll walk through that pretty quickly, and we'll just see how variogram calculation can be done in a more robust, rigorous workflow for understanding spatial data and for doing spatial data analytics with spatial data. Okay, so if you open up that workflow, and I hope this font is good, let me know if you need a larger or smaller font. If you open up this workflow, what you're going to say, thank you very much for the feedback, Chris, on the workflow. I agree. I think there is power to open source as far as being able to build custom workflows too. Okay, thank you very much. And I agree, Pauline, it is a good teaching tool. I really do. The students being able to do this, even with their assignments, I have them load in new data and do their variogram calculations with the dashboard. It's an easier bridge for my students to start using Python too. And before you know it, they start to edit it and they start to learn more Python. Okay, so let's go ahead. We're going to run this workflow together. It's a general workflow. I'm kind of a wordy person. I like to give kind of documentation discussion around variograms. And so I give the equation for the variogram. I talk about the covariance function, its relationship to the variogram. I even give all my observations on variogram calculation right here. I didn't include those in our slide deck because we're being a little bit quick, right? And then some objectives, some information on getting started, and there we are, et voila. So we'll go ahead and import GeostatPy again. We're going to work with just basic stuff here, matplotlib, pandas, numpy, and OS to set our working directory. And let's go ahead, please. I appreciate the thumbs up. Thank you very much for that, Vivian. So we'll go ahead and we'll set the current working directory wherever you have the data file. That's where you need to go. And once you've done that, we can go ahead and load up our data file. So we've got a data frame with our data set. This is sample data. And so that should have been one of the data sets that I provided to you. Let me see right here. Okay. Now, if you're in a situation where, in fact, the data set is sample data underscored biased, I believe you can just switch that out. I think it'll just work. Yeah. And I believe it has the same name, so it should just work. Perfect. So if you're in a situation, I believe I think I accidentally gave you that data set. So let's go ahead and just switch that to sample data biased, and the show must go on. We'll go ahead and run that one. Okay, so now we'll go ahead and we can do a separation by facies, sand and shale, pretty straightforward. Yep, so Emundo, so what you need to do is just change this to sample data biased. I gave you the biased one. Uh, you know what I like about sample data biased? It's a very honest data set. It tells you that it's biased. Okay, so go ahead and just change that out for sample data bias. That's really funny. I thought I'd given you the other one. Okay, so we'll go ahead and we can separate by facies. Then what we'll do is we'll do some basic summary statistics by sand, by shale, and you can confirm. You can look through and see porosity values that range between about 9%, 22% porosity. Mundo, thank you very much for that feedback. So that's working for you. Good. And the porosity for shale is much lower, getting up to about 12% porosity. Okay, so now we can go ahead and we'll do normal score transform. We do that because we're going to do simulation with these variograms. So we got to calculate our variograms of the normal score transform. We'll go ahead and create brand new columns in the data set with npor, nperm, with all of our transformed features to standard normal, 0 mean, variance of 1, standard deviation of 1, Gaussian, beautiful Gaussian shapes. Okay, let's go ahead and let's plot that up and confirm we have what we think we have. There it is, just some nice histograms. Take a look, the original porosity right here, the transform porosity right here. You can see that they're a Gaussian transform. All right. Now we'll go ahead and we'll look at the data sets. Let's go ahead and visualize them. This is all facies put together. This is the sand facies shown right here, and here's the shale facies right here. So really cool. We got our great data set to look at. I appreciate the comment. It's too bad that spatial data sets don't honestly tell you they're biased. I think we'd have to change most of the data sets to have the word biased in them if they're sparsely sampled. Many of them are. Now, I don't mean anything negative by that. It turns out we sample not for representativity, but to maximize project value and answer or reduce uncertainties. That's very different from statistical representativity. Let's go ahead. We'll use Gamvy. The Gamvy function, if you look at the inputs to it, very straightforward. The data frame, the X column, the Y column, the variable column, Tmin, Tmax. And we go ahead and we can set the lag distance, the lag tolerance, the number of lags, azimuth, azimuth tolerance, all of the same stuff that we were just looking at on that dashboard. Okay, so we can go ahead and calculate our variogram right here. Okay, now what we can do, so we run this code, we're able to calculate the variogram. For your practice, I have commented out all of these other variogram calculations by facies, and you can go ahead and load up and use those calculations to try out different variograms. I just provide a single variogram calculation right there. Okay, so this was a walkthrough of a basic workflow to do variogram calculation. Now, if you wanted something more complicated, I do have another workflow that does a lot of stuff like detecting directionality, which I think is really, really useful. Let's see if I can get that. Geostats Spatial, this is it right here. I'm not going to walk through this for the sake of time, but we do some really cool stuff. One of the things we do is we use a functionality built into GeostatsPy to do what's known as a variogram map. The variogram map is effectively calculating a variogram discretized in all distances and directions around a central point on the map. If you look at this axis or this color bar, 0 variogram value means perfect correlation. Well, at a 0 offset distance, you're perfectly correlated. You're comparing the square difference of values with themselves. And as you move away, you'll notice the variogram values are increasing. There's more dissimilarity. And you'll notice by the time you get to this light orange color, that that's the sill. That's the range of the variogram. And so a variogram map, can you see it? If you look at this map right now, do you see that line like this of higher or lower variogram values going like this? The variogram map is an excellent way to detect directionality in your spatial data because you can see the direction over which you have longer range, lower variogram values, whereas in the orthogonal direction to it, what we would call the minor, we have very short range. We have the variogram values rise up very quickly in that direction. A little bit noisy. We have sparse data for this calculation. In addition, in this workflow, what we actually do is we calculate the variogram for a variety of directions, and we use that to figure out the directionality in a really methodical manner. So that's 2 ways we can figure out directionality of our spatial phenomenon, fundamental to spatial data analytics. Okay, I welcome any questions. Once again, people who are jumping in and helping out, I see Michael and others, Brent and Brendan, are jumping in on a question here on an error. Thank you very much. I do appreciate that. That's awesome. Okay, so what we're going to do right now, at this point in the course, I would ask, what's your energy level? Are people still enthusiastic? Are you doing good? Were you able, in fact, to get a break, a little break? I hope during some of that kind of experiential learning, you were able to take a break. And I hope I'm free to carry on from here. And so I'll assume that right now. But remember, you're always welcome to have a mutiny. I've had mutinies in my courses before. People start standing up going, no, that's it. We need a break right now. You can let me know if that's the case. Okay, let's talk about variogram modeling. That's the next thing we want to cover. Okay. Chris said, hell yeah. Holy smokes. Stephanie, thank you very much. A big smiley face and thumbs up. Tobias, thumbs up. I like this attitude of this group. You guys are impressing me. I like that. All right. Thank you very much, everybody. So let's talk about variogram modeling. Now, once again, I warn you, I cannot teach you variogram modeling. I'm going to teach you some very basics, and then you're going to be able to work. Hey, thanks a lot, Michael. You're going to be able to work at playing with the dials and be able to try some variogram modeling out. So please accept like a 50% knowledge about the topic before you run forward. So I do appreciate that. Hey, I'm getting cool graphics now with people saying cool on the channel. That's awesome. What's the motivation? Quantifying spatial continuity is epic, and I think it's super awesome to do, but you have to use it to get the job done, which means estimation, which means some type of prediction with uncertainty, which means we need a model. We can't just quantify spatial continuity. We need a model to move forward. Okay, so once again, I'm not going to cover all the details. If anybody wants more details, I have tons of lectures on variogram modeling. I think my variogram interpretation lecture is actually kind of really cool because I actually take a whole bunch of data sets and I superimpose them. I add them to each other. I actually demonstrate the idea of nested spatial frequencies, and I show how it can actually work with data. Anyway, I think it's awesome. Check it out. All right, variogram modeling. Let's do this. I want to give full credit. Dr. Deutsch, my PhD advisor, I have a couple of slides that I think have still remained from some of his course content that he has freely shared. What a great professor. And so I have one slide here that mostly came from one of his slides, and I do appreciate that. Okay, reasons for variogram modeling. Why can't we just use the experimental points? I calculated an experimental variogram just now. You just calculated experimental variogram. Can't you just put that into the machine? Isn't it good enough? Nope, you can't. You need to know the variogram for all possible H lags. I calculate the variogram for this distance, this distance, this. I need to know the variogram in between. I need to be able to say, if I've got the variogram experimental here and here and here, I need to actually know what the variogram is for any distance. In addition to that, I need to know the variogram for all directions, not just the major, minor directions. I need all of the possible directions in between. So I need a model of spatial continuity that's valid for all possible distances and directions. And you're going to see right away, we need that in Kriging. Spoiler alert. We need to incorporate additional geologic knowledge. People who talk to me about variogram modeling as if it's just fitting points cause my heart to hurt a little bit. And it's because when we work with data-driven approaches like spatial data analytics, we should always be thinking about the subject, thinking about the geology, thinking about those contaminants in the stream or whatever we're measuring, those fish in the ocean. We need to think about them, and we need to realize that they have fundamental physics and interpretations and so forth, and secondary information. Incorporate that into your variogram modeling. That's super powerful. Just awesome if you do that. So, and in addition, the variogram model must be positive definite. And that's fun. That's really cool. You can dig into details and learn about positive definiteness or positive semi-definiteness and so forth. There's a lot of devilish details there. But let me leave it like this. The calculation of a variance from your variogram in a set of points in space must always be positive. What does it mean if you run Kriging, as we're about to see, and we get negative variance? Anybody here ever done a calculation, got negative variance? If you get negative variance, you got to look outside the window and you're pretty sure the universe has just ended. because negative variance is a paradox. It shouldn't be able to happen. The whole point of positive definite variograms and fitting them with a model is that it will ensure that you have valid measures of distance, that all your calculations will be reliable, that you do not end the universe. Okay. All right. Now there's a set of possible positive definite models that we get to work with, and you can put them together. You can plug and play. You can add them together and make a full three-dimensional, two-dimensional variogram model. Now, here are the major types of positive definite structures you get to work with. Behold the grandeur of the nugget effect. This is the nugget effect right here. What's it look like? At 0 distance offset, it says 0. That makes sense. The variogram value at a distance h equals 0 must be equal to 0 because you're comparing data with themselves. The square difference is just 0. And at a infinitesimal, mathematically infinitesimal distance, it jumps up as a step up to the sill, and in all directions, you have no continuity, no information. So its structure is noise. You ever have one of those old TV sets that are tuned out and you just have static? That's the nugget effect spatial continuity model. It's in fact that permeability model I showed you just a little while ago was 100% nugget effect. All right, so the spherical is this. Now it has a very simple equation. It will rise up linearly. It will roll over and it will reach the sill. And at the sill, it becomes constant equal to sill value. Its range is right here, range of 1. That's a spherical. Exponential, whoa, it rises up more steeply, rounds off more gently than the spherical, and it reaches its sill asymptotically. Okay, guys, so there are very different models. And in fact, what's interesting is many spatial phenomena have fundamentally spherical exponential type of behaviors. The Gaussian is super different. The Gaussian, look at its form. Let me ask you a question. Somebody help me on the dialogue here on the Slack channel. Does the Gaussian have more short scale spatial continuity or less than the exponential? Does the Gaussian model have more continuity in the short distances, or does the exponential? Which has better continuity in the short distances? What do you think? I'm getting you to think like a variogram interpreter. Anyone? You know, sometimes I do this with my students. I'll just sit there perfectly still after I ask a question, and I'll kind of like bluff and see, like, you know, I'll see how long they'll wait. They usually answer. Okay, I'll carry on. I'll expect somebody's typing right now. Yeah, the variance is rising slower, so more. Yes, thank you. The Gaussian is more. Holy smokes, is there a lag effect? We do have a delay, right? I believe there's a delay on this. My bad. Geez, and I was even kind of coming after you guys about your enthusiasm. Okay, right now, I want to officially apologize online. Your enthusiasm is awesome. I forgot we had a delay. Okay, thank you so much, everybody. Thank you. Holy smokes. Okay, so Gaussian, everyone's saying Gaussian. Okay, what spatial phenomenon has very good short scale continuity? Is it permeability? No, it's really bad. It's not usually permeability doesn't have great short scale continuity, not in many settings. Yes, Pauline, thank you very much, everybody on that. And FYI, 30-second lag. So I do appreciate that, guys. I apologize. I forgot. Rookie mistake. This is my first time to do one of these. Okay. What feature would often have very good short scale continuity? Usually things like thickness of beds or units. If you tried to build a model of that spatial continuity, that would usually be like Gaussian with very good short scale continuity. So thickness, topography, things like that tend to be, unless you're in the middle of the mountains or something like that. But in general, it has good short scale continuity. Okay. So we have our different types of models. I will not cover the periodic models like the Hall effect and the dampened Hall effect. I actually wrote one of my early papers on the whole story of the Hall effect. That was one of my favorite topics early on in my PhD. Okay. So what are we going to do? What's going to be your job right now? You're going to go ahead and model a set of variogram structures, positive definite structures. You get to pick them, and you're going to add them together. They must add up to be the sill. So you're going to have 1, 2, 3 structures here. You could do nugget effect like this, contribution of the nugget effect. You could do a spherical with a short range of continuity, shown here, short range. You could have another spherical contribution 3 with longer range continuity, and you add them up and look what you get, a superposition of your additive positive definite structures, and that's positive definite. And what's really cool, you've seen the Matrix movie, you're now seeing the Matrix. You can now see spatial frequencies or decompose frequencies or components of variance from your feature, which is very powerful, very, very powerful. And I talk a little bit more about that interpretation. It gets a bit trippy. Okay, so what you're going to do is you're going to go ahead and I'm going to give you experimental variograms in an interactive display. You're going to use multiple spatial structures. You're going to add them together. Now, it's a little bit more complicated than this because we got to do this in full 2D, 2 directions. And so what you're going to have to do is you're going to have to decide on multiple structures. You can pick up to 3 with a nugget effect. The nugget effect is isotropic. It's in all directions. You can pick maybe a short scale, something to describe another component of the variance, in this case, from 0.2 to 0.8, which is 0.6 of the variability. The sill, all of the variability right here. So you'll need another 0.2 with a longer range structure to capture that. You're going to add them all together. Now, if you wanted to do this example right here, just to give you an example, and don't worry, I should expect you not to perfectly know what you're doing. Play with the dashboard, see how you can get it. Okay, we're going to discover it a bit. But to walk through this example right here very quickly, I have which one's the major direction? Well, this one right here, we don't even reach the sill. So that's the major direction, right? And so we look here and we see 0.2 nugget effect, 0.2 nugget effect. I need a 0.2 nugget effect. There's no range parameters on nugget effect. It's just 0.2 nugget effect. Then what I'm going to do is I'm going to say spherical 0.8 to get up to this point right here because there's a major change. We call this zonal anisotropy. We don't reach the sill. We have a pseudo sill. We have to model to there. Then what I can do is I can say, well, in the major direction, I have nugget effect plus 250 meter range on a spherical would give me this shape right here, and I'm good to go. I'm looking really good in the major direction. Right here, what I have is I have about a 400 meter range after the nugget effect, and there's no transition. There's no change. What I can do is I can say 400 meters, and then I'll say 400 meters for a spherical of 0.2 contribution. When I take that, oh boy, I apologize. I just noticed I have a spelling mistake. I have a mistake here. Please just note that. I apologize for that. There's always errors in your notes, right? Because the contributions need to sum to 1. 0.2, 0.6, 0.2 sums to 1. Okay, and this right here is 0.2 to 0.8, so that's 0.6 contribution right there. I hope I didn't cause confusion. Okay, if I go ahead and I say one structure spherical 0.6 contribution of the variance at 400 meters in the minor direction, 400 meters in the minor direction with a 0.2, this is equivalent to the same thing as a 0.8 spherical. When you add them together with the same range, they look like a single structure. And so what we get in the minor direction is this. It looks like a nugget effect plus that structure. In this direction, we want zonal anisotropy. We never reach the sill. So we just put a very large range parameter, and it causes the curve to flatten down. We flatten it down, and we get that effect. Okay, if this is your first time to see this, this is going to be a little bit rough, but let's play around and see if you can get it with the dashboard. Okay, let's do the interactive dashboard. This is super awesome. Okay, so I'll go ahead and open that up for everybody. Where are you going to go in workflows? Interactive variogram modeling right here, this one right here. So go ahead and load that up. I think we use the same data set. Let's see what kind of shape we're in as far as the data set goes. Okay, so I've already loaded it up. It's like a cooking show. I already have the pie in the oven. And so let's see where it is. Interactive variogram modeling right there. Okay, so let me go back up to the top, and we're going to run through this kind of quickly, and then we'll spend a little more time when we do the walkthrough. I think we want to kind of run forward to model, and then we're going to go back and look at the workflow in more details. Okay. Sorry, I forgot to click on the box. Okay, so clicking here, let's go ahead and step through it. We're going to import GeostatsPy like we did before. We're going to go ahead and import NumPy, Pandas, Matplotlib. We need those OS to set our working directory, and IPy widgets for all of that cool dashboard interactivity, which I love. I'm actually a big fan of that now. I've done some stuff in Plotly and also, but I find for really flexible interactive things that works really well. Okay, this data set, you have this data set, I believe. Let me just check and make sure I didn't make that rookie mistake. Data. Okay, do we have it? Yes. Okay, good news. I gave you the right data set that time, so you don't have to change that. Please change your working directory to wherever you have the data set, and you'll be ready to go. You'll be in great shape. Okay, let's go ahead and we'll load that data set up into a data frame. We're now experts in loading data frames. I won't spend any time. You could separate by faces. We've already done this. No, we're not going to this time. We're going to use all faces together. We'll do the normal score transformation again because we have an eye towards simulation. We match the theory of simulation by working in Gaussian space. Has anyone ever told you? Gaussian space is a very happy place. All right. I agree. It is a very happy place. There's so much good math that just works in Gaussian. Okay, let's go ahead and we'll go ahead and do a little preview of our data set with the transformations. We got Gaussian, looking good, looking good. You could do a quick check. It looks good. You could even do QQ plots or something else. Yeah. Let's go ahead and look at the original data values transformed. Everybody already said, look pretty close to Gaussian. Log normal here. That's a big transformation. You know, you might want to check and make sure after the back transform that we have good reproduction statistics. It could get a little bit challenged. There's all kinds of things that can happen when you have extreme transformations, right? Let's go ahead and visualize, look at our data. We're going to do the variogram calculation. We're going to do the variogram map. Ooh, I love those variogram maps. They're so cool. Look at that directionality, eh? That is so good. And you can even see, look at this. In the minor direction right here, do you guys see that there's cyclicity, a little bit of cyclicity, that the variogram goes up and comes back down again? Isn't that cool? I love variogram maps. They're so cool. Okay, let's go ahead and we'll make some observations. We'll calculate variograms. We're going to calculate the variograms in a bunch of different directions. This part we're skipping through. Let's get to the dashboard. I really want to get to that dashboard. We're going to pick a direction. Now, if you wanted to load a different data set and try this workflow, what's really cool is it's designed so you can create all of those different directions and then just pick the major and minor direction by index, 0 through n-1 directions. And from then on, you will be modeling in the major minor direction. So this workflow is very flexible. You could put your own data in and model it. I made it for my students like that. Okay, so we calculate our variogram. Here's the major direction, the minor direction. What do you think? Do you agree? That looks pretty major. You don't even reach the sill. Great spatial continuity. In this direction, much shorter spatial continuity. Okay, so what we're going to do is we're going to go ahead and we're going to take and calculate a variogram, and we're going to just look at it, and we're going to set a very simple variogram model just to get started. But let's go ahead and open the dashboard because I don't want to. Don't look at that. Don't look at that. Stop looking at that. Because I want you to, in fact, do the model yourself. But if you do get really stuck, you can go back and get some hints, okay? Because I don't like people frustrated. Okay, so let's go ahead. And we have this. Now, if you just move something, there you go. Okay. And so if we go ahead, we can look at the variogram modeling methodology. Okay, here's what you get to do. You can change the nugget effect. Look at that. When you move the nugget effect up, the variogram rises in all directions. You can change the nugget effect. You can change the contribution of structure number 1. Now, when you do that, it's going to rise up. If you put some range on it, like maybe like around 600 meters or something, you can notice now that as you move that up and down, look at what's happening. You're moving that structure up and down. And so you could do that. You could have an isotropic structure like that, 600 meters, or let's shorten that up to like 300 meters. And look at that. In all directions, look at that. All directions, it's the same thing. It's isotropic. Now what you can do is you can change the contribution of the second structure to something else, and you could put maybe longer ranges on that. What we're doing here, let me just reduce this a little bit. Now look at what we've done. Is we've made an isotropic variogram with 2 structures. So it's going to look the same in all directions. And if you look really carefully, you'll see a little inflection point right here. First structure, 300 meters, second structure, longer. And so you have a variogram that rises up and kind of rolls over. Now, if you want to create anisotropy, what you can do is take the major direction and increase the range. And I can do that over here too. I could decrease the range in the minor direction. And now if you look at the difference between the major and the minor, You can see this is longer range, this is shorter range, and all these are all the interpolated variogram models for the off diagonal directions. Now, I think I've shown you a bit. Go ahead, don't feel concerned at all about, just play around with it, try some things out. The one thing I would suggest is always make sure the nugget effect plus the contribution number 1 to the first structure plus the contribution number 2 to the second structure, make sure that they sum to 1. If you don't, what'll happen is you'll start modeling above the sill. You see that? We're going above the sill in that direction. Okay, go ahead and play around with this and then we'll talk through it. I will give you 5 minutes until 2:40. Now, if you're getting an error, one thing I think you'll notice is if you set all the contributions to 0, you might, or if you set the ranges to 0. I thought that might give an error. No. I don't know, Tobias. That's interesting. I haven't seen that error before. Does that happen for all possible settings of the dashboard? If you change the inputs, do you get a change? Oh, okay, good. Thank you. Okay, good news. Working for you now. Thank you very much. And I do appreciate you speaking up. We're simulating the classroom environment right now. If anybody has a question, go ahead and shoot it to me on the Slack channel. I'm more than happy to help out. I also want to speak up. I've seen a lot of people jump in with questions. I really appreciate that. That's awesome. Once again, that's one of the great things about the software underground community, people helping each other in digital subsurface. Okay. Good question about the sill. Because of the fact that we have done a normal score transform, we know that the porosity we're working with has a variance equal to 1. And by theory, we know the sill should be equal to 1. And that's why I suggest that we keep the contribution of nugget effect plus the contribution of structure 1 plus the contribution of structure 2 equal to 1. Ensure that sum is equal to 1. Now, if you look at the data, I would agree, Stephanie, if you look at that data set, maybe it's not precisely 1. I don't see it rising cleanly to the sill. The experimental variogram is clearly not rising nicely to the sill. Part of this is because of the strong degree of zonal anisotropy, leading to what we saw in the variogram map as cyclicity in the other direction. What I would do is I would do a quick check and make sure that after Gaussian transform, that the variance in fact is equal to 1. I've had many of cases where I thought I had zonal anisotropy, but the problem was that the transform didn't work and the variance was actually too low. Okay, so these are really good questions, but for the perspective of this workflow, let's just go ahead and make the sum of all contributions equal to 1. Pauline, the refresh effect. Yes, I spent a little bit of time trying to work with the code and optimize it so it would be faster and so that we'd have less of that flashing with regard to the model and the variogram calculation and so forth. Part of the inefficiency with the IPy widgets and the Matplotlib approach is it actually redoes the calculation and the full regeneration of the image every single time you even just touch and move the sliders. And so that is kind of computationally heavy, and it does cause that flickering. If anyone has an idea of how to avoid that. All right, Stephanie, thank you for that. Okay, I promised to get back started at 2:40, and we're just past 2:40 right now. So let's go ahead and work together. Now, we do have a bit of a delay, but if anyone has any inputs, just go ahead and shout something out if you have some ideas for how to model this. Nevertheless, what I'll do is I'll just step through my rationale and my approach to modeling this phenomenon. First of all, I'm going to assume that this is the experimental variogram in the major direction. The variogram map and so forth definitely does support a 0.45 azimuth. Given that, by design and by, well, just us, we have to assume that we're going to expect that the minor direction is 90 degrees from it, 135. So this is all given to us, that we've done a good job of oh man, I just got an update on how to avoid some of the flickering. We're going to make sure we do an improvement. Hey, if anybody's seen a good way to improve these workflows, make a change to the workflow, send a pull request, and you're a co-author on the workflow. This would be super awesome. I do appreciate it. Okay. So, and I do agree with using approaches like R. I do really enjoy doing things in R too. So there's been a suggestion here on making improvement using Shiny. Okay. So let me walk through how I think about this. First of all, I don't see a nugget effect. I see the experimental points extrapolated or interpolated to the origin here, basically reaching at a semi-variogram value of 0. I see no good argument for a nugget effect. Therefore, this nugget effect is going to stay 0 for me. That's the way I'm going to model this. The second thing is I have a structure right here at about 0.6 where I have zonal anisotropy. So I've got a model from 0 to 0.6 with one structure and from 0.6 to 1 with another structure. So I need a 0.6 structure, short range, and I need a 0.4 structure with longer range. And so that's what I know right now, that my first structure is going to be about 0.6 and my second structure is going to be about 0.4. Now, when I look at that zonal anisotropy in the major direction, I can see it's about 300 meters. And so let me just, for sake of argument, I'm going to accept maybe 300 meters isotropic structure. Okay, so let's go ahead and do 300 meters. And now I've modeled, I have no range here. That's why it's kind of jumping up for the first 0.4. And then we can go ahead and we can start to put some ranges here. In the major direction, I think I have zonal anisotropy. Let me start with the minor direction for the longer range structure. Let's just try something. Let's set it to be 300 meters. Well, look at this. In the minor direction, I look like I'm doing very well. I think I'm pretty good as far as this variogram goes already. Now, the major direction, my problem is I have that zonal anisotropy. I've got to put some range here. Watch what happens. If I go to 300 meters, that's not good enough. I need to flatten this off. So watch this, 600, 700, 800, 1000. Look at what's happening. I'm flattening off. As I go longer and longer and longer, I stop seeing an impact from that structure in this scale of 0 to 700 meters. It's still there. I reached the range at 1700 meters, but I stopped seeing it in the window over which I'm interested. I keep going longer and longer range. Look what happens. So the truth is, to get zonal anisotropy, what I'm going to do is just simply set the variogram range to be very large, a very large number, and look at what I get. What do you guys think? Is that a pretty good variogram model? Is that at all like the variogram model that you got? I find it very useful to look at the interpolation. This is 045 variogram. This right here is the 067.5 variogram. This right here is the 090. You see it's interpolating using a geometric anisotropy model, which is super powerful. I now have a positive definite measure or model, I should say, of spatial continuity that's valid over all directions and all distances. That's the whole idea of variogram modeling. Do you want to try something out? I'll tell you what, we could try some things out. One thing, what would happen if I add nugget effect? Well, if I add nugget effect, I could do that. I could reduce one of the structures and I could put a little bit of nugget effect. I'd get something like this and I'm still modeling to the sill. What if I was to actually use Gaussian models? What would that look like? Whoa, ho, ho. What do you think? Is it getting better? Let me remove the nugget effect and let me go ahead and add more contribution there. That actually doesn't look so awful. Now, maybe it's not Gaussian, but it's still kind of cool to try it out. And we could go ahead and try Gaussian for the second structure and see the overall Gaussian shape for that direction, the minor direction. There's a lot of things we can do with this interactive variogram modeling exercise. Let me just very quickly go to variogram modeling right here. Oh, let me see. I'll get that. Right here. Right here. Okay. So this is the overall variogram modeling workflow. Given the amount of time we have and so forth, I'll go very quickly through this. I have some explanations of variogram observations. I explain the concept of nested variogram structures, the analysis, spatial analysis of different spatial frequencies, the components of the variance or of the sill, how we add them together. I even give the equation for the geometric anisotropy model, which you'll see immediately based on the ranges in the major and minor directions, is in fact just simply the equation for an ellipse. Pretty simple stuff, in fact, an ellipsoid in 3D and so forth. So then we'll go ahead and import the GeostatsPy package. We can go ahead and set our current working directory, load our data up. We've already done this, so I'm going to just zip along here pretty quickly. Do the normal score or Gaussian transforms, 0, 1 Gaussian transform to our data set. Visualize it, plot the distributions, look at the plot of the spatial locations, make sure we got the calculation good. We're going to do a variogram map, all using GeostatsPy. Then we can go ahead and calculate experimental variograms. We've already done that. And this part right here where we fit the model. Now, what you'll notice here is these are the model parameters. Now, we did it in an interactive dashboard, but this is exactly what we did. We said we want a 0 nugget, a 0.6 contribution to the first structure, short range structure, a 0.4 contribution to the second one. And we had, in this case, I did 300 meters, 350 meters for the range, major and minor. And I put 400 meters in the minor direction for the second structure. But other than that, it was very similar. I think there was just a difference of about 50 meters or so in what I did with the dashboard. And here's the result right here. Now, if you want a little more nuts and bolts, you'll see that GeostatsPy, what it does is you can make a variogram model object. There's no mystery here. That object is simply a Python dictionary. It's just a dictionary. This is just a convenience function right here for readability of the code. And we can go ahead and create a model that is interpolated for any distance and direction, so we can now plot it and visualize it. So V model is simply for plotting, interpolating a variogram model for any distance and direction, so we can then put it on this plot. That's exactly how I got all of the interpolations for all of the angles too. This is the minor, this is the major, this is the minor, and that's all there is to it. Now, if there's any questions remaining about this geostatistical or spatial data analytics concept of variogram modeling, I welcome any questions on the Slack channel. Otherwise, I'll proceed to the next topic, which is going to be Kriging, spatial estimation. Okay, so what we'll do is we can go back to all of the content from the GitHub account, and we'll go to the slide deck on Kriging now. How's your energy level? People feeling pretty good? Anyone? I know there's a bit of a delay, so go ahead and give me a thumbs up. Maybe I'll like harness your energy. It'll carry me forward. Okay. Awesome, guys. Very cool. Thank you for your participation. Brendan, thank you very much. I appreciate that. And appreciate all your help. Brendan Hall doing an awesome job supporting this conference and really helping out with all of this stuff. I always give full credit. The person who's behind the scenes making it run, there's so much technical details that need to be worked out there. So appreciate that, Brendan. Okay. So awesome. And I can see the delay is now been exceeded, and I'm getting I'm getting like a waterfall of comments. This is great. Thank you very much, guys. Appreciate that. Okay, so motivation. Now, yes, let's keep going. Okay, we need to make predictions away from sample locations. In fact, that's our business. We sample sparsely in the subsurface. I ask the question to my students all the time: what proportion of the subsurface do you sample directly in your setting? And you know what the answer is? What do you think? I know there'll be a couple answers going in right now. Thank you very much, guys. Rocket ship. That's very cool. I think that's Lucas there. Very cool. Okay, thank you very much, guys. What proportion of the subsurface do we sample directly? I mean core data. I mean well logs from a well that penetrates the reservoir or the unit of interest. In oil and gas deep exploration, I tell my students we often sample about 1/trillionth volumetrically of the subsurface. And now our job is to make a prediction after sampling only 1/trillionth. 1/trillionth, yes. And so thank you for that, Fahim. Appreciate that. And so now we have to make an estimate away from the sample data. Sample data 1, 2, and 3. This is the area of interest, the area of study. And our job, our very difficult job, is to figure out what's going on here with uncertainty. That's the motivation. Now, if anybody wants to get many more details about spatial estimation using geostatistical methods like Kriging, please go ahead and jump in and look at some of my lectures on Kriging R. Hey, to the R people out there, gotta love R, using GStat to do that, get the job done. And also here's a Python walkthrough of what I'm about to show you. So if you're interested in getting more details about this, please go ahead and check out this content. Okay, how are we going to make an estimate at that unknown location given these three data? Now, what's interesting, a very simple way to do it would be to use a linear weighted estimator. And so you could imagine the estimate at the unknown location right here would be equal to the summation of the weights applied to all of the data at their locations. Now, there's a little devilish detail here, and that's unbiasedness. The problem is if you could imagine, if we wanted to give less and less weight to the data, and in fact, if you imagine that we deem there's not very good information from them, and we give them low weight, all of them, as that weight goes down, our estimate would go down just by looking at this part of the equation. And that makes no sense. That would be a biased estimator. An unbiasedness constraint would say that we take 1 minus the sum of the weights and we put it on the global mean. This is the simple Kriging paradigm, and it ensures that we have unbiasedness in our estimates. Okay, so this is going to be our estimator. It's going to be based on linear combination of our weights, but guess what's the problem? What are the weights we're going to use? How do we come up with the right weights to use? Well, it turns out if we were to spend the time in one of my lectures, and I do have some of this within my YouTube videos, we could do the derivation of a system of equations, which is called the Kriging system. And this Kriging system, I think probably better communicated in matrix notation, is simply just based on a matrix with the redundancy measures, the degree of correlation between all of the spatial data. Now, for mathematical reasons, we've taken that relationship, the covariance function is equal to the variance or SIL minus the variogram, and we've used the covariances instead. It has more to do with solution schemes to the matrix inversion, but we won't get into that right now. This matrix has the degree of correlation between data point 1 and itself, data point 2 and data point 1, the correlation here, the covariance between data point 1 and data point 3, all of the combinations of the data with each other. Therefore, that is a measure of all of the redundancy between the data, which is super cool. That's very, very powerful. This matrix right here is going to include all of the covariances, spatial covariances, and these come from our variogram model, in fact. That's why we modeled that, between the unknown location and all of the data. So that's telling us about the degree of correlation spatially between the unknown location and the data. So this is telling us about the closeness within the system. Now, if you think about it logically, that is like really epic. Because if I was to try to come up with the very best weights for point number 1, 2, and 3, I would want a measure that would account for spatial continuity. I would want a measure that knew about the nugget effect, about the directionality, about the zonal anisotropy that we were showing you just now. I wanted to have my variogram. Well, these covariance functions do. We're in fact using the variogram and we're flipping it upside down effectively to make it a measure of closeness, a measure of similarity, as opposed to a measure of dissimilarity. We wanted to count for closeness. In other words, if data point number 1 was very close to the unknown location, it should get more weight. This matrix is accounting for closeness. And I care about redundancy because if data point 1 and 2 were moved so they're on top of each other, they should not get the same amount of weight now. They should lose weight because they're becoming completely redundant with each other. If I had 1,000 samples all on top of each other here, they should not get the same weight as data point number 3. Nah, they're all redundant with each other. We need to account for that or we're in trouble. Okay, so that's the concept. Now, let me just list a couple of properties of simple Kriging. If we have a positive definite matrix system, and that's why we use all this variogram modeling that we just showed you, we will have a solution to that system of equations. We can calculate the weights and they will have a unique solution. Okay, but we need it to be positive definite. We need to use a valid variogram model. Kriging estimator is unbiased. We already talked about the unbiasedness constraint using the 1 minus the sum of the weights and applying it to the global mean is what we're going to do. It's a minimum error variance estimator. Yeah, that's why they call Kriging BLUE, best linear unbiased estimator. Sometimes I say glue. I try not to be too proud, good linear unbiased estimator. But it really is, it's best from the sense that it minimizes the error variance estimator. Okay, it provides a measure of estimation, or what I'll call often the Kriging variance. It's the uncertainty in the estimate. Now, let me ask you people, anybody here have a really good friend? Do you have that kind of friend who no matter what you do, what you say will just give you the honest truth? You know what I mean? Like when you're about to send that email, they tell you don't send it. When you get mad about something, they kind of remind you about the other side of the story. That good, honest friend. Let me tell you, Kriging is now your best friend, and it's one of those good, honest friends. Because what Kriging's going to do, it's going to give you the best linear unbiased estimator, but it's going to tell you how bad it is. Isn't that great? It'll give you not only that estimate, but it'll give you a measure of the uncertainty or variance in that estimate. And if you go ahead and say that we'll assume a Gaussian shape, you can get the full uncertainty distribution. We could get into much more details about that. Now, those estimation variances or Kriging variances will range between 0 and the CIL. Let me ask you guys, and I'll just kind of move forward, but let's see what people say. What locations in your space or in your area of interest would you expect the Kriging estimation variance to be equal to 0? Where do you have perfect certainty in space? And conversely, what locations would you expect the Kriging estimation variance to be equal to the CIL? In other words, maximum uncertainty. In other words, you know nothing. Hint, hint. Okay, go ahead and think about that. Go ahead and we'll wait for the lag and I'll go ahead and move forward, but I want to see the responses. Question 1, where would you see Kriging estimation variance equal to 0? And question 2, where would you see it equal to the variance of the problem, the variance of the feature? Okay, what we're going to do right now is we're going to do a little interactive Kriging. Now, I'm pretty proud of a lot of these interactive workflows. This one, I think I'm even most proud of because I think this one turned out really nicely and a great educational tool. Pauline, let's see how fast this runs on your machine. I hope we don't have too much flicker. It's a little heavy, okay? Chris, nailed it, 100% for you. Where do you have the Kriging estimation variance equal to 0? at the data, at the observations, at the location you sampled. Boom, 100%, you get an A+ in my course. Yes, Fahim jumped in too. He said at the location where you sample the core. And Edmundo said, number 2, where would you see the Kriging estimation variance equal to the variance? And Stephanie, Mondo, and others have said when you're beyond the range. And that's exactly it. When you're beyond the range, you know nothing. And if you think about it, Kriging will actually estimate with the global mean and will tell you the uncertainty is the global variance. What is Kriging telling you? Away from the data where you're beyond the range, you can pick a random value from the global distribution, and that's the space of uncertainty. You don't know any better. Isn't that cool? Very awesome. Now, I know there's a couple people here in the audience, because I've seen some advanced questions, who are thinking about all kinds of things, about trend modeling, about heteroscedasticity. I told you I was going to say that word once. Yeah, there's a lot of details. Now, let me just throw something out there because it's good for me. This is my therapy session right here, to use words like heteroscedasticity. If you look at this Kriging estimation variance, it is a function of the CIL. The covariance function at 0 is the CIL, and minus the sum of the weights, those optimum weights, applied to the covariance, the degree of similarity between the sample data and the unknown location. Does the magnitude of the data values appear in that equation? Do you see at any point, does it ask what the magnitude is? And the answer is no. In other words, the Kriging variance is calculated only considering the total variability of the problem and the degree of similarity or spatial correlation between the data and the unknown location with their optimum weights. Okay? In other words, Kriging variance or Kriging estimation variance is homoscedastic. Its measure of variance is invariant to the actual magnitude of the estimate. Isn't that interesting? That's a very interesting thing. It's a homoscedastic estimator. Now, it has all kinds of interesting properties. I kind of throw this out there because I know from the question, there's a few of you in the audience who are kind of seeking deeper knowledge. I welcome you to look at the videos to learn more about the implication issues around homoscedasticity, heteroscedasticity. Plus, we had a request for me to say that word, so I've said it. Okay, what do I want you to do? This is my favorite interactive demo. I want you to spend a little bit of time on it. Why? Because it took me a long time to make it. I want to see it's useful. Okay, so please, what we're going to do is we have a display like this. You're going to be able to change the variogram, but I only give you one structure because you got a lot of things to do here. You're working hard. I don't want to overwork you guys. You're doing great today. You can change the nugget effect, these type of structures, spherical, Gaussian, exponential. You can change the azimuth, the horizontal major and minor ranges. But after that, all you can change is you can change the location of the data. Isn't that cool? So you have an unknown location at the center of the display, right here at 500, 500, y equals 500, x equals 500. Then what you're going to have is you're going to have the data. Data point 1 is blue. Data point 2 is red. You see how the dots on the sliders are the same color. And data point 3 here is green. What you have is you can move those data around. You can change the variogram model. Okay, I think we're good there, right? Now what's super cool is you see this gray outline. That gray outline is the ellipse that describes the range of spatial continuity. If you make it isotropic and short, it's going to shrink into a circle. If you make it long in both directions, it will fill up the whole space. The size of these circles right here are proportional to the weight put on those data. This data point number here, 3, right here, the green data point, gets 0 weight. It disappears. You see that? And I wrote here 0 weight, 0.58 weight, and 0.05 weight. And because I already explained the equation, you now know 0.05 plus 0.58 equals 0.63. I would expect that the remaining weight, 0.37, would basically be put on the global mean. So that's how simple Kriging is going to work, and you can visualize this. This right here is the uncertainty at that unknown location. The estimate is 1.42. The estimation variance is 0.66. Here's the distribution. This is the uncertainty. Your honest friend Kriging is telling you the best estimate, and the uncertainty as a distribution. This right here is just to help you visualize the major direction, the minor direction, and the interpolated variogram so you can understand your variogram that you just picked. Okay, any questions about that? Given the fact we have a little bit of a lag, I'm going to go ahead and keep talking, but if a question pops up, I'll go back to it. What I want you to do is I want you to try things out. I'm going to leave this slide deck up once I walk you through it to get you started. Try 100% nugget effects, see what happens to the uncertainty and the estimate. Isotropic, in other words, the major and minor ranges are equal to each other with a big range, 9,000. Data near the estimate location. Put a data point right on top. One of you said at the data locations that you would expect, Chris said at the observation points you would expect to see 0 Kriging variance. Try that out. That would be super cool. Beyond the range. Awesome. Okay, Lucas just sent me. I hope this is okay to show right here. He just sent me, beyond the range, you know nothing, Jon Snow. Oh my gosh. Okay, sorry. I had a chuckle about that. That was super awesome. Okay, so let's go ahead. And the other thing I want you to do is I want you to use strong anisotropy, move 2 data points on top of each other and see how their weight changes and do the screening effect. Now, I'll get you through everything. I'm going to show you the screening effect at the very end. I'll use a hockey analogy. I don't want to talk anymore. I talk way too much. Okay, so let's go ahead and let's walk through that. Okay, so you can go ahead to the workflows, and we have interactive simple Kriging right here. Okay, now this is like a cooking show. I already have it open and ready to go. Interactive simple Kriging right here. Remember, everybody, friends, this is using GeostatsPy under the hood everywhere. Now, in this case, I did cheat. I made a fast Kriging methodology that just Krigs at one point for efficiency, but I used GeostatsPy kind of parts. I pulled it out. I think I actually put it back in the GeostatsPy as a method to Krig at one single location. Okay, let's see. Oh, let me get back to the Slack channel. I don't want to forget, especially after somebody showed me that. So Emundo was talking about this demo is really good. I lost the widget I found in the late 1990s that would do something very similar. I agree. Definitely not the first to think of interactive workflows within Geostats for sure. No. Okay, so let's go ahead and walk through this. I hope everyone's caught up with me. We're going to go ahead and run this through. I'm wordy. I explain Kriging. I explain the unbiased estimator, the constraint of the 1 minus the sum of the weights. I talk a little bit about trend modeling. I skip through that for this lecture. We don't have time to talk trends. Then I talk about spatial continuity, redundancy, closeness, and the Kriging estimation variance, the properties of Kriging. Very cool. Spatial continuity again. I've got it all there. Okay, so let's go ahead and let's import GeostatsPy. Now we're going to use GeostatsPy to get the job done. And we're going to go ahead and import Matplotlib so we can do all the plotting. I have a little bit of patches from Matplotlib so I can do that ellipse on the plot. That was super cool. I thought that was great. Operating system set the current directory, NumPy Panda, so we can work with data frames and with ND arrays, and the IPy widgets for the interactivity. Very cool stuff. I love it. Now, I told you I cheated. I didn't exactly use GeostatsPy. I created a brand new simple Kriging. Anybody out here who knows about Kriging and simple Kriging, I hope you smile about that name. It's simple Kriging because it's only Kriging at one point for efficiency. That's not a standard thing. Usually we Krig over an entire map, discretized at locations, to interpolate the entire volume or area interest. Okay, so go ahead and run that. I hope that worked for you. We're going to go ahead and we'll make our interactive simple Kriging. Now, we don't have to load any data because you're the data. You get to move the data around. So that's fine. Okay, that's awesome. People are making updates on my workflow live in real time. I'm going to tell you, this is the community. You guys I'm just absolutely stoked right now. This is so cool. Okay, let's see. Interesting. Is that something we should try right now, maybe? Okay, well, let's see if this works, and I'll try it out, and then I want to get people started just so I don't get distracted. Okay, here is the display, and we have our inputs, the nugget effect. You can add nugget effect. You can do contributions. You only get one structure, so please make sure the nugget effect plus I didn't put the contribution for the first structure because we'll assume variance minus nugget effect is the contribution to the first structure. My apologies, I forgot I did that, but that's good. We want the total of the contributions and nugget effect to be equal to the CIL. So I put that by constraint here. You can change the azimuth, the directionality, the major and minor ranges, and you can move the data points around. To instantiate, get the display going, just start moving something around. And remember, you got work to do now. Okay, so what I'm going to do, I'm not going to look at that because I don't get to have any fun. I'm the one doing the tutorial right now. So what I'm going to do is I'll just put it back on. No, where is it? Right here. I'll put it on my assignment for you. This is what I expect from you. 100% nugget effect, try it out. Isotropic with range of very large. Data at or very near the estimation location. Strong anisotropy, 2 data values very close to each other. And then I'll walk you through screening afterwards. I want to give you 5 minutes to play around right now. I'm simulating the classroom environment. I'm pretending I'm standing at the front of the class. Feel free to ask me a question. While everybody is working here, because maybe I'm not a fan of silence. A shout out to all of the undergrad students who are participating today. I know we made invites throughout my university, University of Texas at Austin, to the Cockrell School of Engineering and to the Jackson School of Geosciences. Thank you very much for joining in, guys. Also, I think we have participants from Colorado School of Mines. If you're coming from another university, you're an undergrad or a graduate student, go ahead and just on the chat window, just let me know what school you're from. Did somebody just ask me what I play on Steam? Anybody tried Skyrim in VR? It's incredible. It really is. Rachel is taking my geostats class in the fall at UT. All right, we'll see you there. Hook 'em horns. Oh, nice. Stephanie, where's that located? What's the location of the Institute of Technology? Yeah, I didn't know how to pronounce it. We'll do about another minute. I'm not just idly. Okay, in Germany, very cool. I passed through Germany recently on my way back from Italy, teaching in Florence. Beautiful country, beautiful. Copenhagen, very cool. Nice, thank you for that. Brazil, another university in Germany. Awesome, wonderful. I love this, so cool. Nice, thank you. In a way, I think we can admit like some of this virtual remote learning is kind of cool from the standpoint it is pushing us to kind of more global learning opportunities. Very fun. Okay, another Brazil graduate student. All right, thank you. Thank you, Marcos. Okay. UNAM from Mexico. Juan, very cool, very cool. Got some good friends down there. Okay, undergrads and graduate students, thank you very much for participating. Just wonderful, very awesome. If at any point during your degree program, some of my lecture content is useful to you, I hope you can make use of it. It's all available on YouTube with all of my exercises worked out and opportunity for you to try them out. Okay. Do you guys want more time? Or are you good? I'll give you the option for 2 more minutes and I'll wait 30 seconds. Joining us from Egypt. Very cool. Ali, welcome. Very much welcome. Indonesia. Thank you. Florida. Thank you, Christian. Oh, we have a former graduate student from Dr. Foster in UT. Very cool. Thanks for joining in. And okay. All right, that's about as much time as I promised. I don't want to, you guys are going to think that maybe I'm starting to just try to take a long break and gab the whole time. So what was the job that I gave you to do? Okay, so let's look at this. The first thing I said was try 100% nugget effect and see what happens. Okay, so what would be cool is let me give myself some spatial continuity. So we have pretty strong degree of spatial continuity. The estimate is 2.0. The simple Kriging variance is 0.2. So we do have quite a bit of information at this point. You can see these points. This second point, because the directionality is getting 0.8 weight, 0.11 weight, 0.11 weight. Wow, the sum of the weights is in fact greater than 1, and there's a negative weight being applied to the global mean. It means it's effectively within round off. There's no weight going to the global mean. There's enough information from all the data. Now let's go ahead from there and let's increase the nugget effect. Okay, so up the nugget effect, just watch the weights. Did you see that? Did you see that? The weight of 0.8 to this data, and you know why, because the azimuth is saying the 0, 0, 0 azimuth direction is the major direction of continuity with almost 4,000 meters of continuity. Woo, continuity, lots of continuity. And the other direction's about 1/4 of that at 1,000 meters or so. And so a huge amount of weight. Now look what happens when we increase the nugget effect to 0.1. You see that? It changed by 0.7. This is the massive impact of nugget effect. Nugget effect says in all directions and distances, 10% of the variance is unknown random effect. I don't know. And the result is that immediately things start to move towards the global mean. And we see that the variance starts to expand very quickly. Now look at this. Just check this out. Look at that. The Kriging variance was 0.2, put in a nugget effect of 0.1, and boom, the simple Kriging variance jumped up to 0.3. Now the Kriging estimate stays at 2.0 because this data was influencing the 2.0 and the global mean is 2.0. This is 1.0 here, 3.0, 2.0. So we're not seeing a shift in the mean. We'll see that later. Let's increase the nugget effect. You see that? The weights are falling. Boom, boom. Now when we get to 50% nugget effect, look at this. The simple Kriging variance is now 0.77, a huge amount of uncertainty. We're starting to become quite uncertain. The sum of the weights, if you sum them up, the weight on the mean is now 0.34. We're putting 34% of the total weight on the global mean. We're saying, I don't know that much. I'm starting to lose information. Keep going. Boom, boom, boom. We keep going up. And look at, by the time we get to 100% nugget effect, now the variogram models in all directions are just SIL. That's nugget effect. We have zero weight to any of the data. The weight on the mean is 1. The global estimate is the global mean. The Kriging estimate is the global mean. And the simple Kriging variance is 1.0. That is the impact of 100% nugget effect. We know nothing at this point. Okay. Let's go ahead. So that was the first job, was 100% nugget effect and to observe that impact. Now let's go ahead and remove the nugget effect. And let's now check. You can see the nugget effect is falling. There's a little bit of a step. It's not flickering very much, though. It looks pretty good, actually. Okay. I have a pretty good computer, maybe. I don't know. So isotropic with a very large range. So let's try that. Let's set both of the ranges very large. Let's see what happens. Okay, so now when we set isotropic with very large range, look at that. Simple Kriging variance is 0.05. Look at the uncertainty distribution. Very, very narrow. Great spatial continuity. You can see everything. You can interpolate very easily. And look at the sum of the weights is equal to 1. There's no weight going to the global mean. We have a pretty good idea what's going on. It's a very, very good spatial continuity and a lot of certainty as far as that estimate. Now, if there's any questions or anything as we go along here, please feel free to jump in. I apologize. I have been looking at my slide deck on the other side to make sure I know the problems. The third problem was put a data at the estimation location or very close to it. Okay, what's going to happen? So what we'll do is let's go ahead and drop this down to something more reasonable. Hey, I want to show you something. I want to do something for fun. Let me just show you something really quickly. Okay, let's let this recalculate. Okay, recalculating. I did quite a bit of moves, so it's doing lots of calculation at this moment. All right. Geez, that's a lot. That's really taxing my CPU at this moment. Okay, I think it should almost be there. Okay, good. So we shifted that all down lower, and I apologize. That's computationally kind of expensive, and I would agree. I think it was Fahim who suggested having an execute button that would help avoid this kind of real-time lag effect, and I do appreciate that suggestion. Great idea. Okay, so what we're going to do right now is we're going to move one of our, well, let's go ahead and change this. Let's reduce the range in the minor direction so we can actually see it now. Okay, there it is. You can start to see the range because this distance is only 500 meters right here. We're not really seeing the spatial continuity. Now look what happens if we rotate the azimuth. I think this is kind of fun. If we rotate the azimuth, you see how all the weights are changing? The primary direction of continuity is 0.0675. You see that? We're really seeing how Kriging reacts, how Kriging behaves. Okay, we played around with that. We rotated that around. Let me take data point number 1 and put it right on top of the data location. Put it very close at least. Okay, so I move it up on the X, the 500 meters. The unknown location is 500 by 500. So I can move that up. And now I'm going to go ahead and move that across like that. So the data point's moving across. Look at that. Do you see that? So as I get closer and closer, the uncertainty goes down. The estimate gets very close to look. The estimate is 1.24. Now the estimate's 1.20. As I get closer and closer, the estimate gets closer to the data value. And the uncertainty is decreasing. And when I get directly in the same location, At that point, I would expect the uncertainty will go to zero. The estimate will be equal to the data value. In other words, Kriging is an exact interpolator. It will give you the data value at the data location. Okay, now let's try one more thing out. How's your enthusiasm? Are people still enthusiastic about this? Is this useful? I hope so. What I want to show you is what would happen if we make two data points right on top of each other. So let's go ahead and move this down a little bit. We got a weight of 0.46 on the blue point and 0.03 on the green point. Let's move the green point closer to it. Okay, 0.4, 0.38, 0.27. Now, okay, remember that. That's about 0.6 weight in total. Now let's put them right on top of each other. Look at what happened. Do you see that? What's happened now is that the first data point has grabbed all of the weight, almost all of the weight at 0.5, and the remaining little bit of weight is being applied to the other data point. We're creating a situation as we move them together, they start to share their weight, and one of them that may be a little bit closer, we can make the blue point just a little bit closer, will grab all of that weight. Anybody here ever played hockey? This is an important, very important question at this moment. Anybody ever played hockey? Hockey, one of the big plays in hockey is what's called the screen shot. So what you have is you have the big forward get right in the goal crease with the goaltender and get in the way. Then you pass the puck back to one of your defensive men sitting at the line, and they do a slap shot. They just barely miss the forward, and they get the puck past the goaltender because the goaltender can't see the puck coming. That's the screen shot. And so what we can do is we can demonstrate another concept. It's called screening. Check this out. If we take the green data point and we put it in behind, you can't see it because my program was not made to show negative weight. But if you look really carefully, do you see that? 0.55, 0.09. Kriging is capable of estimating with negative weights when you have screening. Data point number 3 right here is behind data point number 1 with regard to, it is screened with regard to the shooter, the unknown location. Oh, Brendan, thank you very much for the maple leaf. You cheer my heart, man. So cool. Okay, it's screening and it causes negative weights. And that means that Kriging is capable of extrapolation outside of the range of the major and the minor direction. Okay, you know that's field hockey, right? That's not ice hockey. Just to be clear here. Somebody just sent a symbol. I think that's field hockey, isn't it? Okay, which is still cool. It's still cool. Okay, I wanted to kind of demonstrate these different aspects of Kriging. I hope that that was useful to you. What I want to do right now is walk through a much more thorough Kriging workflow, and that will finish up our demonstrations. Now, we're not going to edit or work with there. Hey, howdy, Calgary. We're not going to go through every detail, but I want to prove to you that a pretty comprehensive spatial estimation model can be completed with just plain Jane GeostatsPy and further advertise the package to you and its functionality. Once again, I have lots of documentation up front, and we're able to learn a little bit about Kriging and Variograms, and then we're going to go ahead and import. Remember, this is GeostatsPy Kriging. It's available on GitHub, and it's also available within this course. We'll import GeostatPy, we'll import Matplotlib and Pandas and NumPy to be able to work with our data. Set our working directory to wherever we have our data files being kept. Okay, so set that working directory wherever you put those data files. We're going to separate. This time we're getting serious. It's time to get serious. We're going to separate by facies. So we're going to separate the sand facies, which is 1, the shale facies, which is 0. And now we have sand and shale data frames. Okay, I'm feeling pretty good about this. We're doing some really robust kind of modeling now. We can start doing all of the summary statistics for each one of them. You can comment these out, and you can look at a specific summary statistic like shale. You can see what your shale statistics are looking at, how many data you have. Alistair, greetings to Calgary. And so we'll go ahead and then we'll display our data. These are the distributions of our data. No surprises. You guys know this data set. We worked with it a bunch for the variogram calculation, so we can use our variogram models that we already calculated, right? Okay, now what we're going to do is we're going to visualize the data and see what it looks like. This is facies. This is porosity. This is permeability. This is permeability versus porosity. Woo, what is that? That's heteroscedasticity, guys. Pretty cool, eh? Everyone, that's heteroscedasticity. Very cool. The other thing, too, is anybody who's a geoscientist, what type of depositional setting do you imagine this might be, given we have sand-rich facies and we have shale-rich facies like this? Any thoughts? I will accept anything for full marks on the Slack channel. Let me know what you think is going on as far as this depositional setting right here. Okay, so now we're going to go ahead and do some modeling. We're going to go ahead and we're going to separate by facies. We've already done that. Let's display by facies. This is porosity sand. This is porosity shale. You can see they have distinctly different ranges. I plotted them on purpose with the same color bar so we could all see that. Permeabilities of the sand, permeabilities of the shale, log normal distribution, much more extreme difference even on that. Indicator Kriging, I have not shown you an interactive approach to do that. But let me just give you a couple of points about it. Indicator Kriging is very much similar to simple Kriging, but we do a probability transformation and it allows us to work with categorical variables like facies. All right, Sai, I see you said fluvial, and I apologize if I've mispronounced your name. You said fluvial. I would give you full marks for that. Maybe anastomosing, kind of like the kind of more stable channels. I'm not seeing meanders or anything. It does look kind of fluvial. Could also be deep water channels, right? Yeah, exactly. Thank you very much for that. Fluvial channelized system. Thank you for that, Evan. Appreciate that. Okay. So with indicator-based approaches, we can actually go ahead and work with facies and build a probability-based interpolation of the probability of sand and shale, which is awesome. I'll skip through some of these setups right here. There's documentation here to help you out. We're going to assume some variogram models. Yeah, it could have been deltaic. It could have had maybe a part of the delta. You don't see the distributary pattern, but it could have been deltaic. Sure, I'll accept that. Now we'll go ahead and run this. Now, this is a cooking show. I've already pre-calculated these. These ones are taking more like 20 seconds, 15 seconds to run. So rather than sit here, I'm just going to show you the results for this workflow. It's pretty cool, isn't it? I think it's awesome. I love indicator Kriging like this. We have dense data, so we can really inform these boundaries. And so what do we have? These are areas of, this map right here is the probability of shale. This map right here is the probability of sand from Kriging. If you sum them together, they'll be equal to 1 because it's either sand or shale. They're mutually exclusive, exhaustive categories, okay? So now, look at those maps. Isn't that great? In locations where you have a lot of, in locations where you have a lot of sand information, probability of shale is very low. In locations where you have a lot of shale information, probability of shale is very high. In fact, it gets to certainty as dictated by the spatial continuity model. And we have this probability of sand map, and we have the boundaries where we're transitioning with a transitional probability between sand and shale. That's indicator Kriging, and that's available directly in GeostatsPy to be able to perform that with any number of categories, each one of them having their own variogram models. Okay, I didn't get into indicator variogram models either. There's details we could got into. This is 3 hours after all together. Okay, so now let's go ahead and we'll do Kriging for porosity. And we're going to look at that and see what we get when we do the Kriging. Oh, I ran it. I couldn't help myself. I ran it. I should have just looked at the output. This is going to take probably about, oh, it's fast. It wasn't too bad. Okay, so this is Kriging overall for all of the locations. I believe this was using all of the data. This is Kriging for using all of the permeability data. And guess what Kriging does? You know, your good, honest friend even gives you a map of the Kriging variances. So guess what? You see the bullseyes? Those are locations of 0 Kriging variance. In other words, the data locations. And you see these locations right here. Those are locations where you exceed or you reach a point where you've exceeded the range of spatial continuity and you know nothing, the Kriging variance is coming back to you as the CIL equal to 1 because we standardized, we went normal score. All right, so now we can go ahead and we can do a bifacies type of approach. We can model variograms by sand, by shale, do them all separately, do the job right. And if we do that, this is what we get. We get a model of porosity, continuous porosity and permeability in sand. We get the porosity, permeability in the shale, and we can put them all together right here. And this is it. So if we do Kriging for the categories of sand and shale, and we assign sand where we have a greater probability of sand, we get sand, shale. And if we do porosity by sand and porosity by shale and put it back together, you see the discontinuity at the edge of sand, shale, the interface. This is what's known as the cookie cutter approach to geomodeling or spatial modeling, where we model each of the categories separately using separate data. We don't overlap the data and we put it back together. It assumes a hard, discontinuous boundary between the facies. If that's not good, and you can test for it, in fact, then you would switch to a methodology that allows some type of soft boundary or information sharing. And we could talk about that too. Here's the permeability by facies. You see that boundary between sand and shale. And this is just awesome. These are really nice, beautiful models. This is all Kriging based. I wish we had more time together. I would have got into simulation-based approaches. We talk about global and local uncertainty, pre-drill assessments. There's so much more you can do, all built on the GeostatsPy package. Now, okay, so I had a question here from Chris. Can you create a mask in GeostatsPy based on Kriging variance to eliminate the Jon Snow areas? I love that. The areas where you know nothing. You realize, Chris, from now on, I'm going to use that in my classes. I hope people all know Game of Thrones though. Okay, so what I can say, let me put something out for you. At the locations where you know nothing, like Jon Snow, you're going to estimate the global average. And that's not the wrong thing to do. If you have no local information, the global average is the best estimate. It minimizes the L2 loss function. It's a great thing to do. Okay. The other thing is that people in mining will often use the Kriging estimation variance in order to get at something like the proven, probable, possible type of resource type of assessments. Okay. So people actually often do use them as a measure of local uncertainty to then make decision making. Also to decide where to drill next to maximize reduction in uncertainty. All very powerful things to do. Okay, Chris, thank you very much for that. Now, is it possible to do something very similar using simulations? Oh boy, can we? If you go back to my GitHub repository and you check out my Python numerical demos, all of these are all of the GeostatsPy, and look at that, simulation post-processing for uncertainty, indicator-based simulation. There's all kinds of, this is a simulation approach that makes synthetic data sets. There's all kinds of simulation workflows that are available for you to try out and use GeostatsPy to get your job done. So I hope that's helpful for you, Juan. Thank you very much for that question. Okay, if there's any other questions, go ahead and just shoot. Other than that, what I will do is I will shift to the wrap-up section of this. And look, I'm actually on time. Why am I so surprised? Okay. What we'll do is we'll talk about some course conclusions, some parting remarks. Okay. What am I going to do? I want to make some concluding remarks. There's some important points to make around spatial data analytics, resources moving forward. And because I told you I'm a corporate person, I worked in industry way too long, for a long time. I'm not going to say way too long. I love my time in industry. But because I was there so long, I did get some industry type of behaviors, many of them, which are great. And that includes plus and delta feedback, which I think is a wonderful thing to do. People are welcome to participate as they will. What was my motivation this whole time? What was my sinister plan behind all of this? Hey, Arham, thank you very much for the feedback on the Kriging interactive tool, saying it was cool. I agree. I think it was very cool. My motivation was to promote the use of and contributions to GeostatsPy, some form of open source package to enable spatial data analytics and geostatistics in Python. I think this is super important. I just want to call people out. Matt Hull, Thank you very much. Matt has put out a link on the Slack channel to a survey. So I do appreciate that. Please, people, consider filling out the survey. It'll help us as far as improving the content. Matt, thank you for all you do. You're awesome, man. Pauline, thank you for joining in. It was so nice to have you here. Nice to see you again. Okay, support education of students. I'm big into education. I'm really excited to help people out with education. I had a professor recently from, I think it was from Denmark, no, from Norway, to tell me that I really helped them out with COVID because they were able to use my online resources to help with remote learning. That made me have just a great week. I think it's all about, we're all in it together. We're all about educating and also working professionals. I really love to see that. I do a lot of training with professionals. I love to see them learn. Expand the use of spatial data analytics and machine learning to the subsurface. Would you believe when I visit companies that there's still many companies that are kind of not using a lot of spatial data analytics, maybe using more traditional contouring type approaches? There is an opportunity to improve practice overall. And that's what open source is really great at. We can make data analytics, machine learning workflows accessible to all scientists and engineers. And I'll tell you what, I love seeing so many people learning how to code and doing cool stuff. Concluding remarks. I want to appreciate, once again, anyone who's contributing to the package. Going forward, when you make significant contributions, of course, you become one of the co-authors, you're part of the family, part of the team. We welcome any contributions. And I've seen even today some great ideas. Reminder, what's good? I think we have a lot of workflows that are documented. I am really, really happy, and I shouldn't brag, but I feel really good about all the wealth of workflows with sample data sets to practice getting the job done. I think this can be really helpful to people just trying to get the job done or to learn how to use spatial data analytics. I think the interactive workflows for teaching tools is really a great idea to help out, and I'm seeing great responses from my students. It's all available on PyPy repository, and we've made some efforts around documentation. What needs work? Anyone who looks in the code is going to find issues. Of course, there's lots that can be done with efficiency and optimization. I really appreciate that. There's good things on coding standards in Python. I have done a lot of basic function type of, you wouldn't believe it, I actually had 13 years of C++ full stack development, all object oriented, and I got a little bit lazy here. I was just coding up a lot of functions, very simple things. Of course, we can make it better for expandability, encapsulation, and so forth. Good coding practice, of course. The documentation can, of course, improve docstrings documentation overall. And I love the idea of expanded spatial data analytics, spatial statistics. We have simulation workflows, but I would like to see more multivariate spatial simulations. That'd be really cool. Maybe expansion of LU simulation type of methodologies, MPS for multiple point simulation. We should be doing that. I have students right now working on machine learning based. I know Lucas has done super cool stuff, really at the vanguard of machine learning based geostats. And so I think there's great opportunities to improve the overall functionality. What I tell people is, if you come up with a new method that gives you, accounts for space, accounts for data, accounts for scale, gives you uncertainty, guess what? You became one of us. You're doing geostats, because that's what it was all about. It was a set of tools to get the job done. Now, if Brendan just said in the comment window, if we could do it as a sprint project, I would be right there working with you. I'd be happy to contribute and help. I would love to see something like that happen. Okay, and Lucas, thank you very much for the good feedback. I appreciate that. More resources are available. Please check out my GitHub channel, GitHub repository. I have a lot of stuff there. I literally have Excel documented workflows to doing a lot of spatial data analytics, because sometimes you reach people where they are. And if they can do Excel, you can teach them the subject. And I think that's important. So I have even Excel demos, R demos. I have a bunch of sample data sets, like example data sets anyone in the world can use. I give out a lot of course content. It's all there for you. I hope this doesn't sound braggy. Okay. I also have my YouTube channel. Please check that out. And Twitter, anyone on Twitter, hey, let's, I love that. I love sharing stuff. Very few dog pictures. I promise you a high proportion of technical content that's useful, and sometimes positive messages. And once in a while, a hiking picture, just have to be accessible as a prof and all of that stuff. but most of the time, ask me about the direct consortium. We work directly with industry, myself and Dr. Foster, with some other great professors, Dr. Torres Verdin and Dr. Van Oort. Professors, we always got our hat in our hand, right? We got to support those graduate students. So please consider our direct consortium. We work with professionals in training through DATUM, Energy Data Science Education for Working Professionals. Ask me about that if you like. Plus and deltas. Anybody have anything? What are the pros and cons as far as this? Does anyone have any feedback you want to provide right now? I know that Matt Hall has provided a survey. I do welcome for maybe just a couple minutes if anyone has any feedback of what you liked, what could be improved with this type of tutorial. I think it's a good discussion. Okay, I see a bunch of people saying that they enjoyed the discussion. I saw people say that they enjoyed it, that they're looking forward to using the resources. May I put forward the resources, kind of additional resources that were available to you after the course? It sounds like that was a big comment I'm hearing a lot of. Additional resources that are available to supplement your learning. Okay, I hear somebody saying it was inspiring. You know, I love it. Okay, somebody feels inspired. I'm going to write that down. Inspiring treatment of the topic. May I say something like that? You know, inspiring coverage. Okay. Anything else? The notebooks and with the, okay, so the notebooks, you like the well-documented notebooks? Good. There's a lot more. Check them out. Check them out. Okay, and the great notebook, and that was Florian. Hey, Florian, howdy. How are you doing? Nice to hear from you. Matthew, step-by-step. Okay, so well-documented. Let me put step-by-step workbooks. Okay, thank you very much. Energy and enthusiasm. Oh, I'm good for that. I had a lot of carbs last night, I guess. Okay, energy, enthusiasm. I'm enthusiastic because this topic rocks. This is really awesome. This is changing lives. I'm really stoked about it. I'm always stoked. I really am. Okay, awesome lectures. Marco says he's going to contribute to GeostatsPy. This is awesome. I love it. I want to see people do that. Okay, slightly more detail in the setup to cover the additional packages needed. Okay. So some more coverage on setup. Coverage on setup, kind of the other packages. I agree. I ran right to the prize. I sprinted right to this stuff. I got right to it. Okay. You know what's interesting? So there's a comment around oil and gas. Usually you have sparse data. Now, what I should say is that when it came to variogram calculation, I purposely used a pretty dense data set so we got nice, clean results. It wasn't too much kind of like interpretation issues. I could have definitely provided you, I do have data sets. Look at my data sets in the GeoDatasets repository on my GitHub account. There are a bunch of data sets, some of them very sparse, like a couple of wells and so forth. Okay. So that's a good question. Maybe to more realistic, can I say it? More realistic with sparse data, the challenge, right? I'd agree with that. That's totally fine. Okay, and thank you very much, Brendan. I appreciate you jumping in there, man. You're doing a great job here supporting this. This idea of making a slight tweak, putting continuous update equal to false to avoid the flicker. I think I had it set to true, didn't I? I'm not sure. I'll check on that. Okay, Mondo said the likes notebooks and all of the videos. Let me put that there. Did anybody watch the videos before this class? I wonder if that actually helped people out. Stephanie wants to hear more about theory. Okay, good. I appreciate that. And I acknowledge for 3 hours, I couldn't do it. I just couldn't do it. So more theory. And you know what? I'm going to be right there agreeing with you. Did you use the word? You used the word homoscedasticity, heteroscedasticity, right? Exactly. Stationarity, Gaussianity, the assumptions, maximum entropy, you know, all of these things, right? More theory. I agree with that. I do. A few more applications based on walkthroughs. I must be tired. Walkthroughs with Kriging. I could do that too. More walkthroughs. And it's time. Does anyone feel like I should have spent more time in code, less time in discussing? RM, you watch the videos. Nice. Fabio, you also watch the videos. Very cool. Okay. Let me see. Did I miss any feedback right here? Okay. Okay, and wow, okay. And that might be Brad C. Is working through my spatial data analytics on YouTube series. Thank you very much for watching the channel. I do appreciate that. I welcome any feedback or comments. Okay. A delta. People said I lied when I said I was bragging. Said my openness is refreshing and so forth. I do like to be transparent about my experience, where I came from, and even things like my hat in my hand, trying to get, clearly as a professor, I'm all about funding students. I often am looking for funding from industry and so forth. I don't think it's a bad thing to provide assistance and to just say, hey, if you want to fund students, we're doing cool work. So what are you saying? It's saying not bragging enough. Maybe that sounds arrogant, but not bragging when I said I did. Okay. That's funny. That's really funny. Thank you for that. Okay. Awesome. Thank you, Matthew. Thank you for that. More time. Hey. That's good. You got to talk to Brendan and Matt about that. They're the ones who told me 3 hours. And thank you, all joking aside, thank you very much for all you did and providing me any time at all. I know you fit me in this conference, and I do appreciate that. Thank you, Matt. And thank you, Brendan. If either one of you want to jump in, if Matt or anybody has anything to say, concluding remarks or anything, I've seen a survey. And so, wow, somebody said this is helping them write their thesis. Wow, that's awesome. I love that. Okay, sorry. That's so great. That's so great. Thank you for that. Okay. If anybody else has anything else, what we're doing now is, this is the end of the tutorial. I will simulate as if I'm there in your company, I'm there in your school. I don't just pack up my laptop and run out the door. I end up often like an hour. Actually, Equinor kept me around till like 7:30 one night because I gave a full day short course, and they ended up, I said, I'll stick around as long as you like. And they tested that. They kept me to 7:30 that night, just talking, answering questions. So I welcome the opportunity. I'll hang out here. If anybody has any questions, we'll keep the discussion going. Otherwise, stay safe, friends. Okay.